these energy system analysis and energy modeling studies at different scales with our colleagues at the master's and doctoral levels. On the top of all, I would like to thank Eurosolar Turkey and Professor Dr. Tanay Sıtkuver with everyone contributed to this organization and for inviting us to the conference by giving this opportunity to share our work and for bringing the relevant researchers, institutions all together. As you know, 100% Renewable Energy Conference has increased the range of the dissemination on the renewable energy idea in the society for the ones who admit being a part of the solution but not the problem. It's my pleasure to observe that the conference is organized for the 11th time this year and increased the number and the quality of its content each year. As an extremely hot popular keyword, sustainable development has been the ultimate target for a city compassing to achieve global living standards and raise the accessibility to energy sources. As one of the best practices, the Covenant of Mayors has been initiated in the borders of European Union to develop an alliance between the voluntary municipalities in the desired climate and interrelated energy manners in the year 2008. Covenant of Mayors has focused on three major targets. The first one is combating climate change and adaptation to its negative effects and supplying energy securely, clean, and the most important one is cost effectively. Covenant of Mayors procedure firstly aims to develop a sustainable energy and action plan in 2 years. After submitting this plan to the Covenant, local council of the municipality approves the sustainable energy and climate action plan as the key document in both strategic and operational levels, defining the detailed work plan to achieve the desired climate and energy targets. In this context, the backbone of our efforts is mainly based on building first a reference energy and climate change adaptation system with a technology-rich database and based on economical inputs, environmental parameters, and respective arbitrarily user-defined constraints to develop an urban-based climate change action plan. In practical, considering the energy systems are usually complex, dozens of decision support tools are to be used in such planning processes for each apartment, ship, aircraft, city, region, or country to make our work easier and get these systems analyzed with energy, economy, and environmental aspects in a detailed and realistic way. Just to remind, International Conference, 100% Renewable Energy Conference, mainly focuses on the renewable energy sources and their integration into our lives with higher efficiency and minimal losses. Then, accordingly, we must carefully plan all our processes from primary resources to production, from demand sectors to consumption, including the recycling in all stages within the economic system. Now, in this our session titled Energy Decision Support Tools and Applications, I'd like to welcome three esteemed speakers. Our speakers will share their specializations and their work with us in 15 minutes each. First, Utku Köker. He is a PhD candidate in the Süleyman Demirel University Industrial Engineering Department. Will give his speech with the title A Regional Urban Optimization for Afyonkarahisar, Turkey. And this study is actually the very first sample as an open source multi-regional energy modeling study in Turkey. And then we're going to watch Alperen Sarı. Alperen is a PhD student in Mechanical Engineering Department of Marmara University. And Alperen will talk about an onboard energy and environmental analysis within the framework Green Deal, as a very hot, popular keyword again, as we all know, Green Deal. And lastly, the last speaker of this session is Emre Leblebicioğlu from Marmara University Mechanical Engineering Department, and he's about to finish his master's studies in this area of energy system analysis, simulation, and modeling. And he is going to talk about an energy system simulation of Turkey with carbon neutral scenario, which, and also this study is a specific one, but especially that this is the first implementation of energy plan in regional modeling efforts in Turkey. So I'd like to give the floor to Utku first to give his speech. And in the last 10 or 15 minutes of this session, we are going to take the questions and give the answers accordingly. So I'd like to now give the word to Mr. Utku Köker. Utku, can you hear me?
Thank you very much, Professor Sulukan. It's a great pleasure for me to join this conference. Can you hear me properly, by the way?
Yes, all good, and the floor is yours. Thank you.
Thank you very much. Greetings from Uşak, Turkey. My name is Utku Köker from Süleyman Demirel University, Industrial Engineering Department. I'm currently preparing my thesis on regional energy optimization. The general theme of IRENEC, which is very important, the 100% transition to renewable energy, we have to talk about that very long, but for the sake of the time and the 15 minutes, I'll be getting directly to my presentation. But before starting my presentation, I'd like to congratulate Professor Dr. Tanay Sıtkı Uyar and the organization committee for the 11th anniversary of IRENEC and carrying on this great achievement. And I'm already very proud of being a part of today's event. Now I'd like to share my screen. A moment. Can you see my PowerPoint, sir?
Yes, very good.
Thank you. Our heading is regional energy optimization of Yunkarisar, Turkey, and we'll be talking first the introduction part, and then implementation will come. Then results and conclusion will be the last two sections. The energy is a very common term used in our daily lives, but there are hundreds of subcategories, from energy assessment to sustainable energy, from renewable energy to optimization or simulation. There are a swarm of subcategories. But today, we'll be talking about the energy policy models. The energy policy, when we say energy policy models, we'll be talking about mainly three things: simulation, optimization, and the hybrid methods. But for the sake of time, as I've said, we'll not be considering about simulation and hybrid, since our focus will be on the optimization models. The individuals from operations research and mainly the energy optimization will be so familiar with some such as MACAL, IFOM, WASP, answer times, Flaxus. Why? Because they are main platforms used in optimization today. And when we think of today's life, we have more than one PCs, or we have telephones, handies, which are already computers. But let's think of the 1970s. No personal computers, no handies. The only computational opportunity remains in the universities or the RD labs. So let's think of IFOM. IFOM is an energy optimization program platform, and it is invented, it is programmed in 1970s, and a horde of countries, IFOM models were established from Mexico to former European Union countries. So when it is 1970s, it can only be described as a great success, great achievement, because they are so neatly prepared models and they are still worth analyzing today. After the 1970s, the 1980s and 1990s were under domination of Markov, which was a very powerful program in data entry and output reporting processes. So a swarm of models from Russia to US, from Turkey to United Kingdom, Zimbabwe, or wherever you can think of, a swarm of models all out the world were established using Markov. And honestly, there are a swarm of models for UK, France, and United States, because Markov was a so powerful program. And when it comes to optimization, you have lots of different assumptions and you have lots of models to create. So Markov ruled the world in those 20 years. But let's say something, Markov had some disadvantages. Why? Because you can mostly take diurnal assumptions, I mean day and night models, or you can take a one representative parameter for demand or for whatever it is. But you cannot use more than 2 time slices or 3 time slices. The 90% of the models are using 1 or 2 time slices in Markov. And that was the problem, because simulation was using hourly models and it had a clear advantage over optimization. So optimization researchers demanded those opportunities. And in late 90s and year 2000s, answer times was introduced with some great advantages. First one, the infinite number of time slices were available in answer times. And of course, partial equilibrium model and the stochastic structure, which one is very important over Markov as a great advantage. And also there are Plexus, WASP, and other softwares, but let's say something. They are commercial models, they are commercial products. So if you want to use them, you have to pay for them. And that was a great issue, because for developing countries and for the university students or freelance researchers, funding those programs was a great burden. So an open source tool was greatly desired. What if we could have such an open source program? We could model our works and share with our friends or with the communities, so they could work on them and modify, improve them, and share again with you. That would be a great advantage, but that could not be provided by those commercial softwares already. So some groups, some authorities such as IEA or European Union started some initiatives and like Horizon programs, and some open source efforts was then invested. But still some questions arise, because the last one was the answer times, and migrating the times code to an open source one was a so hard business, because pre-processing of data or calculation of final model coefficients or the model generation means thousands of GAMS code, thousands of equations, and converting all of them to another language is a great business. And some groups took up that business, and osmosis was introduced in 2008. And osmosis was an open source program. Of course, main collaborators were IEA, which was an ETSAP, of course, which was a long tenure program of IEA. What are the great advantages with osmosis for open source models? And there's no funding issue now. You can modify the data files and model files, and there's a continuous development opportunity since then. But why are we using those software? We have lots of different options before us for new investments in technology. We can build wind power plants or biomass or natural gas power plants, but which one will we choose to build? Since they have different inputs and outputs, and since they have different cost figures, we have to choose one of them. But the main thing is the overall cost minimization. But we have lots of different constraints. So to satisfy all of those constraints and to minimize the cost in the end, we have to use optimization. Osmosis, as I've said, is a very great program, currently a great alternative to commercial ones. It first used the GNU Mat Pro high-level language, but then GANS and Splex version was also introduced by Canos. And then the Python version of Osmosis was introduced with Pyomo. And finally, there is this Julia version working with Leap. Why are we using Osmosis? We can build medium to long-term capacity expansion investment plannings with Osmosis. We can build models at regional, multi-regional, and national levels in Osmosis environment. You can build models including heat and cooling, electricity generation, or transport, or if you're crazy enough, you can merge all of them in a giant model, and Osmosis will handle it for you. And our main assumptions in Osmosis, Osmosis is a deterministic linear optimization model in the end, which means there are constraints and there's an optimization function. And this is Osmosis block structure here. When I have a look at this figure, I see that there are 7 columns. And this is in fact shown you for showing the modular structure of Osmosis. And there's an important thing, except the compulsory blocks such as objective costs or energy balance and capacity adequacy, we can omit storage or emissions if our model does not need them. So the model will still run. And this is a great advantage. We can talk about this figure for a long time, but we have a limited time. So I'm passing currently. The Osmosis optimization function is, as I said, the main thing in optimization, because you have to minimize this cost. And what is it? It's the total discount cost according to R, the region, T, the technology, and Y, the time span. But the objective function is not that small, in fact. It is the sum of operating costs, capital investments, technology emission penalties, etc. Of course, we have lots of constraints to satisfy. And I'll not get into the logistics of all those constraints currently, but we have hundreds of different constraints to satisfy in Osmosis and also in times and other optimization suites. And now I'll stop here and tell you about the context of this paper, this project. I have built 2 models today for 40% and 60% renewable scenarios of Afyonkarahisar. We have, I have wanted to make a model of Afyonkarahisar, making zero electricity import from the main Turkey grid. And additionally, I wanted Afyonkarahisar to produce its at least 40% of its electricity energy from renewables at the first scenario and 60% of its electricity in the second scenario. As I said, Afyonkarahisar is a very important city in Aegean region, Turkey, with a dense population. Afyonkarahisar is given in their 2016, which is our reference year. And I have divided the total electricity consumption to 5 subsectors, such as lighting, residential, industry, agricultural, and commercial sectors. And also we have the installed power capacities in Afyonkarahisar in 2016. As we see here, there are solar power plants, wind power plants, and hydropower plants in Afyonkarahisar given in megawatts. And what are the alternative investment options on technology? We have natural gas power plants and combined natural gas power plant, geothermal, wind, PV, biogas, coal, and hydropower plants in our model. And the figures of the costs, the investment costs and fixed costs are taken into account in the models. The figures are taken from the IEA. But before beginning any energy optimization model, we first try to build a REST diagram, reference energy structure diagram, scenario diagram. And we have made it in 4 blocks mainly, which will be enough to manage the Afyonkarahisar region. I modeled Afyonkarahisar scenario of 40% in one model and 60% in another model. We have 2 models in our hands currently. And the results of those scenarios are 40% and 60% renewable energy scenarios are both feasible for Afyonkarahisar, which means Afyonkarahisar has enough potential of renewable energy. So we can build renewable power plants here to satisfy 40 and 60%. There are so slight differences between those scenarios in the outputs, which mean something very important. The optimization program could eliminate the fossil power plants since they are more expensive than the renewable ones currently, beginning from 2016. So the program already chose the least cost power plants, which are biomass and geothermal for Afyonkarahisar. And PV and wind power plants are also kept in reserve for Afyonkarahisar for later use after 2031. Combined cycle natural gas power plants are utilized just after biomass and geothermal. Renewable energy potential of the city is sufficient. We see that biomass and geothermal are steady until 2031 and engaged fully to its max capacity, and natural gas capacities are engaged over time. Carbon dioxide emission curve has a high slope in the end, since geothermal and biomass power plants are firstly engaged, and then as the natural gas combined cycle power plants are engaged over time, the slope slightly decreases. The costs incurred over time, it's so high at the beginning because Afyonkarahisar is not a net energy exporter city, but it's a net energy importer. So to satisfy its own electricity demand, it has built all the power plants to satisfy the electricity demand in 2016. So a high cost occurred, and then the cost curve slightly decreases. Conclusion, we have seen that osmosis is a very powerful program that can compete with answer times or other commercial softwares. Why? Because I have built those models with times and the results are identical. I have put data to osmosis via Momani, which is a very powerful data entry interface, and Momani also proved to be very useful. I have modified the model files of the osmosis, and it's ran very successfully, which gives us a very flexible platform, which is the osmosis. We can edit all the model data, but the model will answer to you according to your modifications. In the core code of osmosis, there are some slight differences between times and osmosis, but you can eliminate those differences via editing the osmosis code. Thank you very much for listening to me, and I'll be answering your questions in the end.
Thank you, Utku Köker, for your contribution and your time discipline as well. Thank you very much on time. So we are now moving to the next presentation that will be given by Alperen Sarı. Alperen is a PhD student in Marmara University Mechanical Engineering Department, and the title of Alperen's presentation is an onboard energy and environmental analysis within the framework of Green Deal. Previously, actually still, we are currently still working on the ship energy systems together with Alperen on PhD program, and previously, sorry, Alperen studied in Barbaros Institute of National Defense University, and Alperen studied on the energy system analysis and modeling of a chemical tanker in MSc studies as well. So the floor is yours, Alperen. Alperen, can you hear me?
Yes, Professor Slukan. Hello, everyone. Welcome to my presentation. I'm Alperen Sarı. Today I will mention about an onboard energy and environmental analysis within the framework of Green Deal. Different studies are carried out by our team in order to reduce the environmental impacts arising from the maritime industry. In order to carry out these studies at a higher level, we also examine the stricter measures determined by the states and union, in addition to the restrictions determined by International Maritime Organization. And today I will tell you about our work on energy analysis of a ship under European Union Green Deal targets. I will make my presentation on an onboard energy and environmental analysis within framework of Green Deal titles, under the titles presented on the screen. The change in global production and the change in sea trade are directly proportional. We can see these figures. Maritime trade is highly affected by political and economic developments at the global level. Tensions such as spread of national trade restrictions, geopolitical conditions and sanctions, environmental regulations, as well as trade wars between China and America can be counted as the main factors in the decline of the growth momentum. You can see it here. With the addition of the COVID-19 pandemic to the stagnant economy experienced in recent years, it seems that there was a great decline in the economy and maritime trade worldwide in 2019 and 2020. And it's expected in the report published by the United Nations Conference on Trade and Development that 2021 will achieve a breakthrough with a recovery. And when we look at the global greenhouse gas emissions, the transportation sector constitutes approximately the fourth of the total greenhouse gas emissions, while the greenhouse gas emissions from the maritime sector account for 3% of this. And the European Union has an important place in the world trade, as it has the richest and largest economy in the world. Most of the European Union trade, both between its own member states and with other countries, is carried out by sea. And considering the carbon emission restrictions, shipping is one of the few industries today that doesn't have binding measures to reduce carbon emissions. In addition, no payment is made due to the carbon emission pollution. However, maritime in Europe cause high carbon emissions. According to the Europe's leading clean transport campaign, Group Transport and Environment, if maritime was a country, it would be the 8th country emitting the most emissions in Europe. The European Union is known for its sensitivity to environmental and social sustainability issues, especially the fight against climate change, reduction of greenhouse gas emissions, use of renewable energy since the 1990s. Took these sensitivities one step further in November 2019. It has presented a package of initiatives, a commitment to take decisive and ambitious steps in environmental and sustainability issues, the European Green Deal. And in this study, it's aimed to perform energy and emission analysis and modeling of a chemical tanker ship using a decision support tool with the reference energy system concept within the framework of the European Union Green Deal 2030 and 2050 targets. And this is the RES reference energy system flowchart. RES is a flowchart showing the current status from each primary energy source to each end-user request through various conversion and processing steps. This scheme is defined for a moment in a given time period, for example, 2020 or 2025. And a reference scenario is created and developed to compare existing technology or energy requirements with alternative scenarios to be developed. And in this study, the energy system of a chemical tanker ship has been analyzed. This ship was built in Turkey in June 2011. This ship owned by Transal Shipping Company and can carry a total of 26,000 deadweight ton and 29,537 meter cube cargo. In the reference energy scenario, which is constituted after the scanning of the demand and demand technologies, process and conversion technologies, and resource in the chemical tanker ship, meets 14 demands in total by 187 technologies. And different approaches are utilized to plan and optimize the energy system as a whole in terms of energy, economy, and ecology aspects from the engineering point of view. And various energy modeling tools have been developed to date on both micro and macro scale, such as single apartment, building, city, country, or region. Some of these modeling tools are showing in the slides. And we use many of these softwares in general and ship analysis we have done at the National Defense University, Beykent University, and Marmara University. But in this study, we prefer to use the LEAP. LEAP old name is the Long Range Energy Alternatives Planning System, and new name is Low Emission Analysis Platform. Is a commonly used energy modeling software tool for energy policy determination and climate change mitigation assessment developed by the Stockholm Environmental Institute. The LEAP model is one of the widely used energy decision support tools for evaluating energy consumption and greenhouse gas emissions in the home, trade, transportation, and industry sectors around the world. To calculate the energy consumption, 1 year data and information from a chemical tanker ship were received from Transal Shipping Company. In line with the determined parameters, 2017 was chosen to create the basic scenario with the information provided from shipping company. All energy demand and process conversion technologies in the energy system of a chemical tanker ship are defined to LEAP. Then the information obtained was entered in LEAP, and the energy consumption for the reference year was determined. The total primary supply of a chemical tanker ship is 220 million gigajoules and is shown in the table. The total demand of the chemical tanker ship is 171 million gigajoules, and we can see in the table too. Energy process, conversion, storage, and transportation phases. As we can see in figure and table, the main demand for a chemical tanker vessel is utilized in main propulsion with the value of 104 million gigajoules, and electricity generation, heating, ventilating, air conditioning, and heating demands follow the main drive propulsion. And now we are looking for the scenario, alternative scenarios. We have 3 different scenarios. First of all, I want to give you about the business as usual scenario. In business as usual scenario, without taking any measures, a situation analysis was carried out between 2017 and 2050, considering that the demand for the maritime sector will increase by 3% every year. And in the business as usual scenario, a chemical tanker ship emitted 30,000 metric tons of carbon dioxide equivalent in 2017, while the emitted carbon dioxide emission in 2030 increased to 44,000 metric tons of carbon dioxide equivalent. And in 2050, it will be 80,000 metric tons of carbon dioxide equivalent emission. And we can see in the table and figure that the amount of carbon dioxide emissions emitted from a ship will increase by 1.5 times in 2030 and 2.5 times in 2050 compared to the reference year. In this scenario, an analysis has been made in line with the European Union's Green Deal goal of reducing the carbon emission rate by 55% compared to the 1990 level, but we don't have the 1990 is value for this ship. So we are making our analysis compared to the reference year. In this analysis, which is made considering that the demand for maritime will increase by 3% of every year, and the amount of carbon dioxide emission from chemical tanker ship within the scope of the European Union Green Deal targets in 2030 should decrease to 19,000 metric tons of carbon dioxide equivalent. And in this scenario, in addition to the European Union Green Deal 2030 targets, the 2050 targets are also included in the analysis. In this context, the chemical tanker ship is aimed to emit zero carbon emission in 2050. In order for a chemical tanker ship to reach its zero carbon emissions target by 2050, after achieving the European Union Green Deal 2030 targets, the amount of carbon dioxide emissions should be reduced to the 13,000 metric tons of carbon dioxide equivalent emission in 2040 and 7,000 metric tons of carbon dioxide equivalent in 2045. And finally, at 2050, it will be the zero. And conclusions. The maritime sector stands out as one of the sectors where the least steps have been taken towards reducing the amount of the carbon dioxide emissions. And the European Union wants to lead the maritime sector and to be the first continent in the international area by taking the maritime sector into the scope of the sectors that will make zero carbon emission with its Green Deal goals. In this context, firstly, efforts should be made to achieve the Green Deal 2030 targets. In addition to conducting research and development studies to enable the use of clean and sustainable alternative fuels until 2030, it's considered that success can be achieved by taking measures to increase efficiency in operational, technical, and shipbuilding stages. In the operational sense, the use of scrubbers is increasingly widespread to increase technical efficiency, while using methods of selecting short ship routes and using wind and currents to increase efficiency. And in the shipbuilding sector, it's aimed to reduce carbon dioxide emissions by increasing efficiency with methods such as reducing body friction and design optimization. And another alternative is it's considered that the use of the clean and sustainable alternative fuels will be the definitive solutions for achieving the European Union Green Deal 2050 targets. For this reason, although the use of hydrogen as the most suitable fuel comes to the fore today, there is currently no sustainable and clean energy source to meet all the energy needs of ships. To achieve the Green Deal to 2050 targets, all stages of the maritime industry, including fuel suppliers, work together. And thank you for listening to me patiently. If there is any question, I can answer. And thank you, Associate Professor Sulkan.
Thank you, Alperen. So just as a postscript, as the researchers of this study about the chemical tanker, I would like to express our gratitude to Captain Umut Bozkurt for his guidance, technical and professional support, and sharing expert knowledge. And I would like to celebrate his birthday today and wishing all the best for the captain and his beloved ones. So now we can move to the third and our last presentation in our session today. This presentation will be given by Emre Leblebicioğlu. Emre is a master's student at the very last points of his master's studies. Hopefully, is about to finish his study in Marmara University Mechanical Engineering Department, and Emre is going to talk about an energy system simulation of Turkey with carbon neutral scenario. So the floor is yours, Emre.
Thank you so much, Professor Sulkan. Hi everyone, I'm glad to be here with you, and today I'm going to present energy system simulation of Turkey with carbon neutral scenario, which is part of my master dissertation. Let me share my screen. Before I start, I would like to express my gratitude to my supervisors, Professor Uyar and Professor Sulukan, for their support finalizing this study. Now, before can you hear me? I have a bad connection now.
Yes, pretty good. Yes.
Okay, first I want to talk about the outline of this presentation, and this is a brief outline, and I would like to start first a brief introduction about clean energy transition, and after that I will mention energy overview of Turkey, methodology, and scenarios. Of course, there is a reference scenario, reference energy scenario, and 75% renewable energy scenario, which is also a carbon neutral scenario. And result and conclusion, I will mention all of these things I will point out. And I hope that you will able to understand how to perform the high share of renewable energy system at a national level by the end of this presentation. Now, clean energy transition is everywhere. Actually, it's happening. It's currently happening worldwide, and we can see this everywhere, and we can see this in the numbers even. Total renewable energy capacity reached almost 2,800 gigawatts in 2020 worldwide, and the wind and solar energy capacity were also 733 gigawatt and 713 gigawatt respectively. And that's why planning and simulating an energy system at a national level is significant to perform high share of renewable energy system in the electricity production. Then governments have ambitious policies and strategies to accelerate the clean energy transition from fossil-based sources to renewable sources. Aim of this study basically analyzing the Turkish energy system and show how to perform, how to implement carbon neutral energy system for a country. And to do this, actually, the model that I used is a Harvey simulation energy system model. And this Harvey simulation gives the most realistic solutions, most realistic results also. And different scenario options were implemented, but in this presentation, I'm going to just mention the carbon neutral scenario. Technical analysis and feasible studies were also discussed in this study, and there are some evaluation parameters such as power capacity, instant power capacity, renewable energy share, cost, and CO2 emissions. And results were compared with reference energy results, reference scenario results. Now let's look at energy overview of Turkey. Turkey is still dependent on fossil fuels in electricity production. Even though the renewable energy capacity passed half of total energy capacity, but the share of renewable energy is still in almost 30% in power generation. Feasible energy potential. Actually, energy potential of Turkey. Actually, we need to know this subject we need to know the feasible energy potentials by sources, because while we are establishing our scenarios, we have to set a limit for capacity expansions. And actually, feasible energy potential is the one of these limits, actually, and that's why this to know feasible potential, energy potential is significant before starting to establish scenarios. 2023 energy goals of Turkey, and this is 2023 is the important year for Turkey, and the government has solid and concrete energy goals. And I wanted to just point out this because by 2023, the share of renewable sources in electricity generation was estimated to reach 38%. Energy Plan software program is the Howard simulation program used in this study. And the normal energy plan simulation is an input-output model and it gives the Howard results, Howard simulation. It was developed by Aalborg University, Denmark, and it is used for energy system analysis at national or regional level. Also, it also performs technical and market economic simulations. I used this. I chosen this software because Howard simulation gives the most realistic results, and also we can evaluate energy system in many aspects by this software program, such as technical analysis, feasibility, costs. That's why Energy Plan is the software program which was used in the study. There are inputs of Energy Plan, like energy demand, power plant capacities, costs, energy sources, simulation strategies, and the software gives some outputs: energy demand, power plant capacity, resources. Now, the reference energy scenario, 2018 was chosen as a reference energy scenario, and as you can see, installed capacity, electricity installed capacity by sources in 2018, still in that period, renewable energy capacity it was less than half of total electricity capacity. Here there's real data and energy plan model output, and this is a model validation. Before we start different models, we need to validate reference energy model, and as you can see, the difference is in an acceptable limit, and this shows that our model is valid, was established well, and we can examine other scenarios over it. And fuel consumption and CO2 emissions of reference energy scenario. Renewable energy share of electricity production was 31% in 2018, and electricity production, renewable energy, and 69 terawatt hour per year. And also CO2 emissions is so high, 144 million ton CO2 emissions in 2018. The cost of reference energy scenario, and we can also analyze the cost of the scenario and compare with carbon neutral, the cost of carbon neutral scenario. And as you can see, the total annual cost is $23 billion almost of the reference energy scenario, and variable cost, fixed operation cost, and annual investment costs are different parameters in this section. Now 25 and 75% renewable energy system scenario, which was implemented for the year 2053. As you can see, there are actually capacity expansions were performed in consideration of many parameters such as political and time limitations. Also, as I mentioned before, the feasible renewable energy potentials were also considered to determine the installed capacities of these sources. As you can see, this is solar PV, and by the way, also nuclear power plants were were considered in this scenario because nuclear power plants are carbon-free energy technologies and also have high capacity factor, and the government of Turkey has a long-term nuclear power plant policy and agreements about that, and that's why in this scenario I wanted to consider also nuclear power plants, and that's why actually our scenario is the 75% renewable energy scenario, because the rest of this amount belongs to nuclear power plants. Now I want to show you the general outputs of this scenario. As you can see, fuel consumption was decreased by this scenario, significantly decreased, and as you can see, the carbon dioxide emission is quite low, almost zero. Actually, this small amount emissions belong to biofuels. Actually, there is a small emissions because of biomass, and as you can see, there is a biomass consumption also. Now I would like to show you the difference between reference energy scenario and carbon neutral scenario. At solar PV, there's a huge difference between these 2 years, and also as you can see, indigenous and as you can see, coal power plants were phased out in this scenario, and natural gas power plants, installed capacity of natural gas power plants were not decreased so much, but the share of natural gas was decreased so much, and it makes up just a small amount, 5% of the overall electricity production. And the cost analysis of the 75% renewable energy scenario. In this section, these are unit costs, unit capital costs, and operational time of each type of power plant. These are important parameters to determine, to find the overall annual investment cost, variable cost, and fixed operational and maintenance cost. And now overall investment cost is almost $600 billion, but of course this is the investment for almost 30 years, and annual.
Emre, last 2 minutes, please. Okay.
Okay. Annual total cost is $26 billion of the carbon neutral scenario, and the fixed and operational cost and variable cost is quite low, and I will show this in the results. And as you can see, the difference between these two scenarios, reference energy and carbon neutral scenario, power plant capacities and CO2 emissions and fuel consumptions, and total investment annual costs. And the variable cost is quite low, as I said before, and because the fuel consumption decreased, and that's why the variable cost also decreased in this scenario. And conclusion, just the high biomass and storage capacity is necessary to perform the high renewable energy share, and that's why nuclear energy was considered also, because there is a although there is a huge capacity of biomass in Turkey, but it's hard to implement, and it's a challenging process, and that's why the nuclear power also is an option used in this study. And the time limitation and lack of concrete goals and strategies are the biggest drawbacks to implement in the rest scenarios. Heat and transportation, hydrogen production can be also investigated by the energy plan model, and this study gives a healthy outline for the authorities to shape Turkey's future energy system. Thank you so much. If you have any question, I will be happy to answer them.
Thank you, Emre. And now we can move to the end of this session. After a very beneficial session, according to me, we try to come up with the indigenous experience on energy decision support tools and their applications with 3 different modeling platforms. I think that this area of expertise will be more and more visible, together with the increasing importance of energy planning efforts, determined emission mitigation targets, and technology adaptation processes. So these studies prove that we have the energy system analysis, simulation, and modeling capabilities to develop indigenous or national reference energy systems and emission inventories for every single energy system in every scale, doesn't matter if required. It's obvious that this will be a serious requirement for the municipalities in following days, if we admit being a part of the solution, but not the problem. Finally, I would like to check if we have any questions, but as far as I can see from the Zoom platform, we still don't have any questions so far. And I'd like to thank all 3 speakers and our listeners for your time and attention. And I wish peaceful and healthy days with my best regards. And Professor Uyar, by your let, I'm closing this session. Thank you.
Thank you, Dr. Sulukan. Your efforts, your contributions in energy decision support tool development, beginning from your PhD to today with your students, we are just creating a capacity to deal with the European Green Deal perspectives, because planning the future of 2050 is very important. Thank you very much for our students, contributors, and everybody. Thank you for moderating this session also. Thank you very much. Now, the next session will start at 12:15, and with the 3rd conference presentations, we have about 15 minutes break. Evet. Toplantımızın bugünkü ikinci oturumuna başlıyoruz. Bu oturumumuzu sesim duyuluyor herhalde.
Evet hocam, buyurun.
Evet.
Dinliyoruz.
Peki. Bu ikinci oturumumuzda bugün Sayın Doğancan Beşikçi'nin Eurosolar Türkiye'den moderatörlüğünde Aleyna Yıldız, Merve Topçu, Simay Erdem, Beykent Üniversitesi öğrencileri ve 9 Eylül Üniversitesi'nden, İstanbul Teknik Üniversitesi'nden Özge Baltıcı ve Mert Çolakoğlu olacak. Doğancan Beşikçi, söz sizde. Moderasyonu siz yapıyorsunuz. Buyurun.
Thank you, Professor.
I have spoken Turkish. I'm sorry. Yes, okay. Anyway, it's clear.
Okay, good afternoon, everyone. This is Doğancan Beşikçi. I'm a mechanical engineer who is working in heat exchanger sector and also part of the Eurosolar team, proud part of the Eurosolar team, and will moderate this session for next 1 hour. In this session, we are going to see 5 interesting paper about energy decision support tools and applications. The general topic is of our session is energy decision support tools and applications. Let me check the schedule. According to our schedule, Aleyna Yıldız from Beykent University will be the first presenter and will present the paper named Renewable Energy Modeling in Izmir by using Answer Times program. Then Merve Topçu from Beykent University will present the paper named Renewable Energy Modeling in Bursa by using Answer Times program. And after the modeling for provinces, Simay Erdem from Beykent University will present the paper named Design and Analysis of Passive Buildings using the software Energy Plus and Open Studio. The fourth place, Özge Baltıcı from 9 Eylül University will present the paper Photovoltaic Energy Forecasting via Artificial Neural Networks and Support Vector Machine Approaches. And the last presenter, who is Mert Çolak from Istanbul Technical University, will present the paper named Energy Exergy and Environmental Analysis and Multi-Objective Optimization of a Solar Renewable Energy Multi-Generation System considering the summer daytime climate conditions of Mediterranean region in Turkey. According to our timetable, each presenter has 13 minutes for the presentation. And for the questions, we are going to use 10 minutes period in the end. I think I talk about the structure of our session. And now, Aleyna Yıldız, the microphone is yours.
Thank you, Hocam. First of all, I want to introduce myself. I am Aleyna Yıldız from Beykent University. I am a mechanical engineering student, and today I will talk about İzmir. I will talk about aim of research, energy overview of Turkey and Izmir, potential energy of renewable energy in Izmir, answer times, and I will introduce my reference energy system of Izmir, and I will talk about my results. If I should talk about aim of research, we made this with data about between 2018 and 2033 data to current situation to create an energy model, to have a decision support model, and to be able to see our energy carriers to demands. Energy overview of Turkey. When we see the Turkey energy overview, we can see almost 60% of energy carrier from fossil fuels, and only 40% of renewable energy. And when we came to Izmir, we see that Izmir has different than Turkey, because in Izmir we have 55% fossil fuels and 45 of energy carriers from renewable energy. And why I choose Izmir? I choose Izmir because of geopolitical location. It is very useful for renewable energy. I will show you. It is very, very rich according to renewable energy carriers in Izmir, renewable energy resources. Energy generation. I will also talk about this, but Izmir is the most important and most important city in generation part in Turkey. Sectoral distribution. Izmir also have a lot of factories, a lot of companies, and a lot of sectors in the city. Sustainable life and understanding. It means when we see the other cities, all of them has not any sustainable action plan, but Izmir also have. And energy potential of Izmir. When I start to my study and when I finished, it was February, and there were 18 of natural gas power plant, 40 solar PV, 58 wind turbine, and the total capacity was more than 4 megawatts. And there are more 100 industrial factory or fabric, and approximately 10 gigawatts of electricity is produced. And there were 120 power plant in total in Izmir. Answer time, it is a software. In the first session, Mr. Kökner told about this history, but I want to give some little informations too. This software has some parameters, and there are a lot of parameters in the software, and we can have scenarios like local, global, or specific region, economically, environmentally, timely, technologically, for energy, about energy. And my reference energy model is here, but I will show you from my model because it doesn't full here. My model is here. It is the reference energy system of Izmir. In this reference energy model, we can clearly see the resources, primary energy carriers, our conversion technology and demand technology, and the result demands. How we did this? As I said before, there are 18 natural gas central here, and imported gas is a resources here, and our primary energy carrier, natural gas. But these directions goes to two final energy carrier. It means we use natural gas in Izmir to heat energy and the electricity. I will also talk about the demand technologies and demand, but first of all, I want to explain this part. In solar energy, there were 40 energy plants, energy PV in Izmir. And also it goes to electricity because we produce electricity in these PVs. And the wind turbines, it is most important renewable energy source in Izmir because it's very huge energy, and we have 58 wind turbines in Izmir. And gasoline, LPG, diesel, like all cities we have. produce manure for agricultural demands, and it's also electricity production here. And exported electricity part is affected all our demands. In demands part, we determine these demands according to İzmir. What this means? This means, first of all, we listed all factories, all companies in İzmir and what they do, what they use, the machines. Then we listed them. Then we have a connection about these energies. For example, in residential and commercial part, this not is only about factories or fabrics. For example, residential commercial illuminating demand. These bulbs we are using in our houses and also our stores, our places. Television equipments too. The part is about the houses and the commercial part. But when we came to industrial part, we have some machine factories, marble factories, food factories, tobacco factories, and this tobacco factory is the most important factory in İzmir because it is the biggest one. The chemical demands like a lot of chemical factories in İzmir, ceramic parts, milk parts, industrial vehicles demand. Sorry. Here, I didn't mean the vehicles, electrical vehicles. I mean the factories of which does something to vehicles. And textile demand and city service demand. This city service demand is the city demand actually. For example, street and traffic light, cable car, and BİSİM. BİSİM is a bicycle model in bicycle project model in İzmir, and subways. And when we came to this part, you can see light commercial vehicle, city bus, diesel car, gasoline, and LPG car. These are all our transportation demand, and it is same. It is not same with other cities because steamboat is not in all cities. But this part, city bus, diesel car, gasoline car, LPG car, is same with other cities too. Now I am going back to my presentation. And you are seeing this data here. I won't make you bored this all of these data, but I will explain them too. When we are doing this study, we also calculate maintenance and repair costs for all renewable energy centrals, and we calculate also these demands which will have in the future, which have in the past, according to some reports, some government reports. And when we enter these data to answer in time, we see that İzmir is growing according to Turkish growth rate in renewable energy part, and the demands will be enough to generation electricity in İzmir. Thanks for listening to me, but before I finish, I want to say something. First of all, if I had some pronunciation mistake, I'm sorry because I was very excited. And I want to say thank you for our attendees. And I want to say thank you for Mr. Beşikçi because we learned too much thing in this study from him. It was very pleasure. And I want to say biggest thank you to Tanay Sıtkı Uyar, Professor Dr. Tanay Sıtkı Uyar, because when we are doing this study, I was he motivated me very well, and he support us too much. That's why I want to say thank you. Thank you for listening to me.
Thank you, Aleyna. Thank you for all your good thoughts. And this is very good to begin to your academic life. And please do not stop it. So it will be better if you work hard. Right now, we finished first presentation, and the second in the second presentation, I'm presenting Merve Topçu from Beykent University. She will present the renewable energy modeling in Bursa by using Answer Times program paper. Floor is yours.
Merhaba hocam. Hemen ekranımı paylaşıyorum. Görebiliyor musunuz ve duyabiliyor musunuz beni?
It is perfect. It is clear.
Okay. Hi, I am Merve. This project is my graduation project. I am mechanical engineering at Beykent University. Content, I aim of research, biogas, potential of agricultural organic waste in Bursa, answer times, introduction to reference energy system of Bursa, and results. Aim of research, Bursa province agricultural organic waste, waste-based biogas determination of potential. In addition, we will examine the potential of animal waste and urban waste to be able to see energy development of city of Bursa between 2018-2033 in data by considering the development plans according to current situation in order to create an energy model, to be able to create a decision support model, to be able to see and show energy carriers and demands which are belong to Bursa province. Agricultural waste in inventory. In the districts far from the city center of Bursa, the source of income is agriculture. In addition to agriculture, there are canned food factories in Karacabey and Mustafa Kemal Pasha districts. There are more than 10 factories in this region, including tomato paste and canned peas. Intense pulp and waste are produced in factories. An average of 10-15,000 tons of waste is generated from each factory. Some of these wastes are used to animal feed, some are used in garbage dumps, and the remaining part is left in its area. Therefore, the potential agricultural waste, especially tomatoes, highly canned goods such as peas. It's an important raw model for biogas plants. Let's take a look at the agricultural waste table. As you can see, while peas took at the first place, in the pulp amount in Bursa, the second was in tomato. Here, I will talk a little bit about livestock sector in Turkey. There are usually small farms in Turkey. These farms have high production costs and low productivity. The animal waste problem in Turkey is actually collection. Disposal method is to lay on the field or to spill waste in empty areas. Let's take a look at the animal waste table now. Here, cattle took at the first place both in the province of Bursa and Turkey. Finally, let's move on the urban waste inventory. Bursa province produced 100,000 tons of sewage sludge generally. Municipal waste in Turkey treatment sewage, market waste, and food industry waste, the amount of methane to be obtained from this waste depends on the type of amount of raw material. Let's take at the table. Waste sludge ranks first in Bursa. In Bursa, we get the most energy from natural gas, secondly from hydraulic, and thirdly from coal. Bursa has 16 natural gas power plants, 4 solar PV, 8 wind turbine. Total instant capacity is 2,974 megawatts. More than 100 factories, approximately 18,893 gigawatts, 52 power plants. I will summarize these parts a little because Aleyna explained it in great detail. We work on the same project with Aleyna, only your cities were different. I don't want to take much of your time. Let me briefly talk about Bursa's demands. Industrial machine demands include, for example, automotive, textiles, service demands, drilling machine, compressor, transportation demands, city bus, gasoline car, industrial marble demands, residential commercial demands, natural gas heater, television, regulator, pedal box, like the example given by Aleyna. Before I finish my presentation, I would like to thank you, Professor Dr. Tanay Uyar, for giving us this opportunity. I am also grateful for his support. Also, Mr. Beşikçi, thank you for listening.
Thank you, Merve. Thank you for all your good thoughts. Now we are continuing to third presenter, Simay Erdem. She is from also Beykent University, and she will present her paper named Design and Analysis of Passive Buildings Using the Software Energy Plus and Open Studio. Floor is yours, Simay.
Thank you. I will share my screen. Hello, I am Simay Erdem, a fourth grade student at Beykent University, Department of Mechanical Engineering. Today I will talk about my work on passive building design and analysis, which I prepared under the mentorship of Professor Tanay. If we talk about the meaning of passive design is an approach to building design that use building architecture to minimize energy consumption and improve the thermal comfort. Although we cannot achieve 100% passive design vision in every building, applying the passive design approach to the widest possible scope, it will reduce the energy use of the building, the shape, position of the building can increase the comfort of the building occupants by taking advantage of the specific energy forms in the desired location and by offering protection from unwanted energy forms. And a passive house requires very little energy to maintain a constant minimal temperature. In this sense, such buildings are almost passive as they need almost no active heating or cooling to stay comfortable year-round. Excellent insulation and highly efficient heat recovery system make this possible. Passive design's principles are well known in engineering as effective strategies for achieving a goal with the little or no input. So what makes passive buildings so special? Quality levels of insulation materials, well-insulated window frames and glasses, design and construction without thermal breach, and airtight building envelope, and finally, highly efficient heat or energy recovery ventilation systems are indispensable for passive buildings. The design of any two passive house in different locations can be quite different. This may be due to the different requires, the condition of the building and the climatic conditions. The guiding principle is, however, is to reduce peak loads to the point where the building can be heated or cooled with fresh air that must be brought in to ensure good air quality in all cases. When this is done, both suitable are a highly efficient heat recovery ventilation systems can transfer more than 75% of the perceived temperature from system, can transfer more than fresh exhaust air to the fresh incoming supply air. For example, on a 0 Celsius day, such systems can use the stale exhaust air heated to 20 Celsius to bring cold incoming air to the least 60 Celsius without the use of any active heating. There are several conditions for a building to be named passive, some of which are as follows. 50 kilowatt hour per year or 10 watts per square meter of usable living space. Energy demand should not exceed 120 kilowatt hour per square meter of usable living space per square meter in all domestic applications, such as heating, cooling, hot water, and domestic electricity. Air tightness should be a maximum of 0.6 air change per hour at a pressure of 60 Pascal. For thermal comfort, it should be met throughout all living areas, not more than 10% of hour in any year above. Lights must have an efficiency value of 65 lumens per watt or higher, and the color rendering index at least 8. Thermal comfort is a highly subjective and complex field of study. So passive design, we can add 4 indoor factors that affect thermal comfort. These are air temperature, air humidity, air velocity, and surface temperature. The Energy Plus program, which I have used in my own analysis, is a whole building energy simulation program that engineers and architects use to model energy consumption for heating, cooling, ventilation, and lighting, as well as water using buildings. And OpenStudio is a software application used for building energy analysis used in building information modeling. In the project, the building consists of 4 office and lounge type closed area as open offices. Therefore, all areas will have similar properties and homogeneous thermal conditions. And these are lengths of the building, data of the analysis, and general features are presented in this page. In the analysis, weather files were used for existing cities, and annual simulations were made by Energy Plus for ideal weather loads related to the weather file. Ideal air loads means that the performance of the HVAC system is optimized so that the thermostat values are provided by the HVAC system. The front and back views of the current building are as seen in the figures. The data you see in the upper right corner are the building and isolation materials used on the walls, mezzanine, and between floors in a classical building in Turkey. Taking these into consideration, firstly, analysis was made together with the U values of the materials. In the lower right corner, the materials with high U values in terms of isolation selected in accordance with the passive building design are used based on the data. A second analysis was carried out. As I mentioned on the previous page, the same is done for the roof, window, and ceiling. The materials are used here are as shown in the right. The building is divided into two thermal zones as halls and offices. Usage, lighting, and equipment loads are calculated and presented in the table below. Regarding thermal zones, the table provides the zone summary. The results of the existing building analysis are presented as side and source energy, district cooling and heating, average and minimum outdoor air, and heat gain. Analysis results of a classical building are presented in the table below. Analysis results of the new building are shown in the table. The simulation performed for 24 hours and 365 days by entering the outer layer properties loads, schedules, thermostat values of the building, and weather data provided resulted in 7,376 megajoule per meter square energy consumption for the existing building. To see the difference in the case, changing the materials used in the wall, roof, and floor, as well as the selection of triple glaze windows, reduced energy consumption to 4,689 megajoule per meter square. A reduction of approximately 36% is achieved with the only envelope material change. And this means 30 out of 90 in the LEED certification system points. Thank you for taking your time and listening to me.
Thank you, Simay. Now we're continuing to Özge Baltacı. Özge Baltacı is the next panelist, and she will present her paper named Photovoltaic Energy Forecasting via Artificial Neural Networks and Support Vector Machine Approaches. Floor is yours, Özge.
1 minute, I can't. Good afternoon. I'm PhD degree student at 9 Eylül University, Mechatronics Engineering Department. I will try to present my presentation about PV energy forecasting via artificial neural networks and support vector machine approaches under the headings shown in the slides. In recent decades, many renewable energy systems, particularly photovoltaics, are becoming an important source for power generation and have been installed all over the world. However, frequently varying output of PV because of weather data, including irradiation and temperature, soiling, cloud cover, etc., make it an intermittent and unreliable source when connected to grid. For this reason, output forecasting plays an important role in the energy generation and implementation of solar power systems. Until recently, conventional and empirical solutions have been applied in traditional way to predict the solar energy. However, when the results of these approaches are examined, insufficient accuracy and other limitations are detected in the predictions obtained by traditional methods. To overcome these limitations, to deal with uncertainties, and to handle the shortcomings of these traditional methods, artificial intelligence-based techniques come up with their strong and certain effectiveness. Artificial neural network and support vector machine approaches are both artificial intelligence forecasting methods which maximize the accuracy of results of the real-world applications and gain the upper hand about execution speed and time. Our study aims to compare the forecasting capabilities of ANN and SVM approaches by providing the almost 2.5-year historical data from the solar PV plant located in Simav, Kütahya as input. Predictions of the higher accuracy can be achieved by SVM using PV measures with weather data including irradiance and temperature. Results show that the SVM model performed better than ANN model. An SVM is a machine learning algorithm based on statistical learning theory and the principle of structural risk minimization, which was presented firstly by Kortz and Wapnick in 1995. The network structure of an SVM is given in a tree structure in the slides. SVMs have been successfully implemented for various purposes so far, such as image retrieval, fault diagnosis, text detection, and regression problems. The main idea of SVM approach is transforming the nonlinear input data to an area with high dimensional properties to find a hyperplane via nonlinear mapping. Generally, the characteristics of the SVM method can be briefly stated as considerably precise and robust, able to model complex nonlinear decision boundaries, less prone to overfitting in comparison with other models, exhibit a compact description of the learned model, and potential of implementation in pattern recognition, regression, and classification. In recent years, SVM modeling approaches have been implemented extensively in the fields of solar energy and can range from single to hybrid and complex models. Zandabody stated that SVMs have been frequently implemented and got wide acceptance since 2009. Their article contained a list of 75 publications. 47 of them were found for the time period between 2015 and 2017. Wu and Liu developed 5 SVM models with various input attributes to estimate monthly mean daily solar radiation by considering 13 years meteorological data for 24 stations all over China. Studies have demonstrated that machine learning approaches outperform traditional statistical methods. The authors concluded that the SVM methodology may be a promising alternative to the traditional approach for forecasting solar radiation at any location for which air temperatures are available. SVM has been successfully used to address many forecasting problems. INA SVM was used to estimate daily solar radiation based on the duration of exposure to sunshine in China. Generally, the SVM models presented good performance and significantly outperformed the empirical models. However, the developed SVM model was preferred due to its greater accuracy and simplicity. The other SVM model developed and compared with empirical models. The results show that SVM models achieved 14 to 26% greater accuracy. Another application of SVM and ANN models for forecasting solar radiation in Saudi Arabia was investigated. According to root mean square error, the coefficient of correlation and the magnitude of relative error, as well as the speed of computation for the algorithms, the SVM approach was considerably more accurate during computation and rapid in forecasting radiation. Kazam aimed to design and implement SVM for the management of energy generation based on experimental work. The experiments achieved a value which indicates the predicting model is remarkably close to regression line and a well data fitting to the statistical model. Besides, the proposed model achieved less mean square error in comparison with other related works. In its history, artificial neural networks have gone through 3 landmarks. The first in 1943 with the work of McCulloch and Pitts, who were the first to address the subject and to develop the initial concept of artificial neurons. Later in 1960, the perceptron network won space for Rosenblatt's work but was soon discredited because of limitations in dealing with problems that are not linearly separable, the disadvantage of single-layer perceptron network highlighted by Minsky in his work. After this drawback, just a few researchers were developed in the area until 1980s. However, in that decade, the development of the backpropagation algorithm has rekindled researchers' interest. After that, advances in the areas such as economics, health, computing, engineering, and among others, the artificial neural networks have their best structure and functioning based on the human brain. Their aim is to emulate the brain ability to solve problems. Hyken defines these networks as follows. A neural network is a massively parallel distributed processor made up of simple processing units, which has a natural propensity for storing experimental knowledge and making it available for use. These networks have been applied in several tasks, such as pattern classification, function approximation, prediction of parameters, system optimization, and so on. As mentioned in the study of Pradhan and Panda, even though the main input of the PV system is the solar radiation, still there are other factors like temperature, angle of tilt, soiling, and shading which affects the efficiency of the PV module. In our study, an experiment has been conducted to analyze the effect of irradiance and temperature on the power output of the TechPens PV module by using the dataset collected from SIMAV Kütahya. The dataset is used as historical data to predict the future solar energy that will be produced by a determined photovoltaic system. The data from the different inverters are put together in the same dataset. As all the inverters are from the same PV module and they have similar range of power values, the total dataset consists of 1030 rows and 19 columns. The first column is the month and day, the second on the total energy generated, and the rest of the columns are different inverters' values. The rows are the daily data. As at almost 3 years, there are above 1,000 points of solar energy data. In this study, the energy values taken from the small power plant were brought together with the temperature and radiation values at the date the values were recorded. The results obtained in this way were then compared with the results produced by running the same algorithms with energy values alone. The ANN models have been tested with different training algorithms. In the ANN model, we are working on the data are separated for 70% training set, 15% validation set, and 15% test set. In this slide, the results obtained when using the PV values together with the temperature and irradiation values are compared with the results obtained only from PV values under different training functions. In this slide, the regression values of training, validation, and test data are presented. When considered the graphs in the previous two slides in numerical terms, the RMSA values of the model and the actual and predicted values are shown in this slide. By using kernel and SVM approach, nonlinear classification is achieved efficiently. Two different kernels are used in our study, and the predicted and actual values are shown in graphs. The RMSA values of the results obtained with linear and Gaussian kernels are shown in the table. The use of linear kernel in the PV dataset supported by temperature and irradiation values gave the best performance, and the RMS value was recorded as 0.0618. Summing up the results, machine learning has the potential to provide a more accurate and efficient solution in forecasting the energy output as it can be observed from the model RMS values. While the accuracy rate of the model is 96% in ANN, This rate has increased to 98% in SVM. SVM algorithm with linear kernel function has an advantage accuracy up to 94%. SVM algorithm with linear ANN method yielded 87% accuracy with the Bayesian regularization training function. Both methods showed excellent performance, but SVM showed slightly better accuracy for energy estimation. As a conclusion, this paper aimed to perform a comparison study of prediction data system of PV output power by using ANN and SVM techniques. The results show that the SVM is better than ANN in predicting energy output. The performance of SVM approaches, when compared with the results provided by ANN, obtained interesting improvements in the prediction system. It can be concluded that SVM method can predict PV energy with higher estimation accuracy and shorter computation time. My presentation ended here. We would like to express our respect to TechPen Holding, who generously shared the data of its power plants in Simao with us, and our valuable audiences who attended the session and patiently listened to our presentation. Thank you.
Thank you, Özge. Thank you for your this good presentation and study of yours. Now we are continuing the last presenter, who is Mert Çolak from Istanbul Technical University. And Mert Çolak, floor is yours.
Thank you very much. I will share my screen now. Okay, can you see my presentation and can you hear my voice?
It is all clear.
Okay, thank you very much. Good afternoon. My name is Mert Çolakoğlu. I'm a PhD student in Energy Institute of Istanbul Technical University. I would like to present my study named as Energy, Exergy, and Environmental Analysis and Multi-Objective Optimization of a Solar Renewable Energy Multi-Generation System, considering the summer daytime climatic conditions of Mediterranean region in Turkey. The content of my presentation is as follows. I would like to start with introduction, then system description and analysis, and I would like to go to design variables selection and multi-objective function, then presenting the results and discussion, main conclusions of the study, and the references. So the problem definition, let me start with introduction. The problem definition of this study is the increase in energy consumption, climate change, high temperatures, and severe aridity in Mediterranean region of Turkey. So considering these climatic conditions in the Mediterranean region of Turkey, the energy-related critical utilities are power, cooling, and fresh water, especially in the summertime, and green hydrogen as the clean energy carrier for today and for future. So as you can see in the figure 1, here, the photovoltaic power potential of Turkey, you can see that the rectangle is on the Mediterranean region. So the solar power capacity and the potential is very high at that region. So this abundant renewable solar energy can be used for a concentrated solar power system. So multi-generation systems, what is multi-generation systems? Is basically multi-generation systems are the energy conversion systems that can produce more than 3 useful utilities at the same time, like power, heating, cooling, hydrogen, fresh water, etc. So conventionally, power generation systems produces only power, while cogeneration systems produces generally power plus heating, and three-generation systems generally produces power plus heating plus cooling. So a multi-generation system produces more than 3 of the useful utilities. And in literature, it was shown that multi-generation systems are more efficient than the 3-generation, cogeneration, and single-generation energy conversion systems. So literature review in this study showed that no investigation of solar-based multi-generation system for the summer climatic conditions of the Mediterranean region cities of Turkey for the production of critical utilities have been done until now. Therefore, our novel proposal in this study is development of a novel 100% renewable solar tower-based multi-generation system and investigation considering the summer daytime climatic conditions of the Mediterranean region of Turkey and some selected cities in that region. So analysis of this study is done with energy, exergy, and environmental analysis. Also, a detailed parametric analysis and multi-criteria, multi-objective optimization is also performed. So when you look at the system description, you can see in figure 2 that at the top part of the figure, this is the topping power cycle, which is a solarized open gas turbine cycle. So it's based on a heliostat field and the solar tower, so that this gas turbine cycle works with solar energy. And this configuration includes an intercooling and also regeneration. So also, first time in this study, 2 organic Rankine cycles are coupled to this topping power cycle to utilize both the waste heat from the intercooling section and waste heat from the exhaust section. So this is the first time that a study couples this topping cycle with 2 ORG cycles. And this system also includes other subcycles like absorption cooling cycle for cooling, multi-effect desalination for freshwater production, electrolyzer for green hydrogen production, domestic hot water chamber, and industrial process heater. So the multi-generation products, the useful utilities of this system are power, cooling, freshwater, green hydrogen, domestic hot water, and industrial process heating. So when we look at the analysis, by calculating from the available climate data, we calculated that the average daytime, summertime climatic conditions of Mediterranean region are 28 degrees Celsius in terms of temperature and 800 watt per meter square in terms of direct normal irradiation from the solar energy. So in terms of thermodynamic analysis, mass, energy, exergy, and concentration balance equations have been written and applied to all processes in the system. And the system is simulated with EASE engineering equation solver software. So as the performance indicators, in terms of thermodynamic ones, energy efficiency is defined as the total energy output, total energy value of the useful products divided by the total solar energy, and exergy efficiency is defined as the total exergy values of the useful products divided by the total exergy, solar exergy input. And a recently defined thermodynamic performance indicator for multi-generation systems in the literature is EQF, which is exergetic quality factor, which is defined as the total exergy values of the useful products divided by the total energy values of the useful products. And environmental analysis is done based on the CO2 emission savings, because this system uses solar energy to operate and it saves CO2 emissions compared to a comparable natural gas-fired power plants. So emission savings consist of 2 parts. One part is due to the power generation, other part is due to the other heat-related utilities. So for comparison of the power side, combined cycle power plants are used because they are widely applied worldwide at a commercial scale. And for the heat-related utilities, commercial boilers are used as the comparison. And also the CO2 emission factor of natural gas is used for this calculation as the reference system. So the selection of design variables and multi-objective function, as you can see in table 1, the most important design variables of this multi-generation system are pressure ratios of 3 power cycles, which are the Brayton cycle, ORG 1 and ORG 2, and intercooling temperature of the Brayton cycle, and the top brine temperature of the multi-effect desalination system for freshwater production. So these are the design variables of this system. And multi-objective function. So in order to optimize the system, a multi-criteria, multi-objective function is created by using the energy efficiency, exergy efficiency, and EQF simultaneously with the weighting factor. So these weighting factors are alpha 1, alpha 2, and alpha 3. So you can weight them. In this study, we consider these weighting factors as equal. When we come to the results and discussion part, so firstly, the simulation is calculated in the base case scenario with the base case values of design variables, and the performance values are calculated accordingly. And then these design variables are set freely within the ranges, of course, and the system is optimized with a multi-criteria, multi-objective optimization. So as you can see here, all the performance indicators are improved significantly in multi-objective optimum case. And also the optimum values of these design variables are different than those of the base case. So these two aspects shows the importance of the multi-objective optimization of energy conversion systems. Also in table 3, you can see the input and output values of the base case and multi-objective optimized case of the system. So for example, here you can see the increase in energy and exergy values of the products dominates the increase in input rates, which shows a more optimized case, enhances the efficiency of the system so that the design is optimized compared to the base case. Also, a parametric analysis is done in this study, considering the selected different cities for considering their summer daytime climatic conditions. So in table 4, you can see the selected cities in Mediterranean region of Turkey. So these are the representative cities, Antalya, Hatay, and Kahramanmaraş. So their irradiation DNI values, respective DNI values, as you can see, increases from Antalya to Kahramanmaraş. And also the average reference temperatures are also increases from Antalya to Kahramanmaraş. So these data are used for the calculation and the parametric analysis. So in figure 3a, you can see the change of exergy efficiency with respect to the pressure ratio of Brayton cycle. So exergy efficiency reaches a maximum at an optimal Brayton cycle pressure ratio. As you can see, for example, here, there is a peak in this curve at a certain value, and performance is highest in Kahramanmaraş. So from red one, Antalya, to blue one, Kahramanmaraş, the performance increases, as you can see. And the optimal pressure ratio for Brayton cycle increases from Antalya to Kahramanmaraş. So as you can see here, the peak points is here for Antalya, and it goes to right and then further right for Kahramanmaraş. So it's at the higher values. Optimum point comes to the higher values. And in figure B, another graph is plotted for net power generation of the system with respect to the pressure ratio of Brayton cycle for selected cities again. Net power generation increases with increasing pressure ratio of Brayton cycle. As you can see from left to right, the net power output increases. And again, performance is highest in Kahramanmaraş with the blue color, as you can see, compared to Hatay and Antalya. So another plot is done by considering the average Mediterranean region conditions, as you can see here. So in figure 4a, emission reduction, emission savings versus pressure ratio of OREG2 is plotted, and also for the different OREG1 values. So as you can see in 4a, emission savings increases continuously with increasing pressure ratio of OREG2 from left to right. And also pressure ratio of OREG1 has a positive effect on emission savings. So as we increase the OREG1 pressure ratio from red to blue, the emission savings also increases. So the similar analysis is done, this time for exergy destruction of the system, total exergy destruction rate of the system. So the exergy destruction rate decreases with increasing pressure ratio of OREG2. From left to right, you can see that the exergy destruction rate decreases. Also, pressure ratio of OREG1 has a positive effect on the decreasing exergy destruction. So from the red color to the blue, you can see that as we increase the OREG1 pressure ratio, the exergy destruction decreases, which is the improvement of performance. Also, performance analysis comparison is done for the selected cities with the considered climatic conditions. So as you can see in table 5, the performance indicators of energy efficiency, exergy efficiency, EQF, and emission savings, CO2 emission savings, are presented for Antalya, Hatay, and Kahramanmaraş. So as shown, energy efficiency nearly remains similar to each other, but just decreases very slightly. This slight decrease comes from the average temperature, the reference temperature of the cities. And the exergy efficiency, on the other hand, increases significantly from Antalya to Kahramanmaraş. And also EQF increases from Antalya to Kahramanmaraş significantly. And also the similar trend for emission savings, it also increases from Antalya to Kahramanmaraş. So the performance of this system in different cities, performance is highest in Kahramanmaraş and lowest in Antalya among analyzed cities. This is mainly due to higher DNI profile of Kahramanmaraş, which enables higher receiver outlet at solar tower and turbine inlet temperature. So to conclude, in this study, a novel solar tower-driven renewable energy-based multi-generation system is proposed and analyzed in terms of energy, exergy, and environmental viewpoints for the summer daytime climatic conditions of the Mediterranean region of Turkey. So both the system, proposed system itself, and also the analysis itself are novel. And multi-generation system at optimum conditions can produce 525 kilowatt power, 1.2 kilogram per hour green hydrogen, 0.34 kilogram per second fresh water, 44.4 kilowatt cooling, 137.1 kilowatt industrial process heating, and 1.47 kilogram per second domestic hot water. And the performance, thermodynamic performance of the system is 49.7% energy efficiency, 39.6% exergy efficiency, and 57.1% exergetic quality factor at optimum conditions. And also while producing these beneficial outputs and showing that performance, system meanwhile saves emissions because it works, as I said, it works on solar energy. So it saves emissions compared to the fossil fuel-based systems. So at optimum conditions, this system can save 266.1 kilogram per hour CO2 emissions. So in terms of city performances, the highest performance is observed in Kahramanmaraş and lowest performance in Antalya, mainly caused by the DNI characteristics of these selected cities. So here are the references that have been utilized in this study. And I would like to thank you all for your attention. And also I would like to thank to all members, all the contributors who made the IRENEC 2021 possible. Thank you very much.
Thank you, Mert, for your this good study. Right now, we finished all the panelists. All the presentations are finished now. And let me check the questions if we have any. Right now, we don't have any questions from the attendees. We have another 10 minutes, but as I can see, there's no questions still. Okay, we can finish our session in here. Thank you for all for your good presentations and studies. Thank you for the contribution for IRENEC 2021. Thank you for also this Eurosolar team to make it possible this conference one more time. So I'm giving the microphone to Professor Tanay for the next sessions.
Thank you. Thank you, Doğancan. Thank you very much. And thank you for all your efforts from the undergraduate, graduate, and now your contribution together with our other colleagues, which I have thanked already, about the energy decision support tool development for Turkey and cities. And now together with your contributions, we manage this. Thank you very much. Thank you for the speakers also, my students, and Mert Çolakoğlu and Özge Topbaltacı. The future is yours, and we have this European Green deal, as you know, and this is for 30 years, when you will be 50 years old at that time. So it's time for you to contribute further to this transition, European Green Deal transition. And what you are doing now is all related to this. Thank you very much. So now we will continue our conference after a lunch break at 2:15 p.m. See you at 2:15 p.m. for our last session and closing session. Thank you very much for your attendance. Evet, sonunda 4 günlük konferansımızın yani son oturumuna, 4. günün. Okay. So now finally we are in the 4th day of our conference, and we are going to have the conference presentations, the 4th group. Finally, we are approaching to the end of our conference, the closing session. Now, I would like to invite our General Secretary of Eurosolar Turkey, Mr. Anıl Türkünoğlu, to moderate this final session. The floor is yours. You have about 1 hour, 15 minutes till 3:30 p.m. Yes,
thank you.
The floor is yours.
Let me quickly introduce myself first. As Taner Hoca already stated, I'm the Secretary General of Eurosolar Turkey. Also, I'm a mechanical engineer and a professional in the energy sector for 5 years now. Today, we will have 5 presentations from our presenters. They are Büşra Yılgın from Kocaeli University, Levent Akbulut from Başkent University, Nurayni Sunusi from International University of Cyprus, Rania Hamemi from National Engineering School of Tunis, and Fehin Tijesu Babalola from International University of Cyprus. So our first presenter is Ms. Yılgın, Büşra Yılgın from Kocaeli University. You may have the floor. Büşra Hanım.
Hello.
Hello. So you have 15 minutes to present your paper.
Okay, thank you. I can share my screen. Can you hear my voice?
It looks good now. You can start.
Okay. Hello everyone. I am Büşra Yılgın and I am graduate student at Kocaeli University. I will present you our study use of waste heat emitted from a fuel cell in thermoelectric modules. If I'm going to talk about the content in presentation, it's introduction, principle of fuel cell, pros and cons of fuel cell, and also general information about the thermoelectricity. And lastly, I will talk about our work, material and methodology, and also results. In recent years, energy consumption has been increasing due to factors such as population growth, development of industrialization, and people's desire to live in comfort. Due to the environmental pollution of fossil energy resources and the decrease in their reserves, interest in alternative energy sources is gaining momentum. In addition, efficient use of energy is also very important. In this sense, the recovery of waste heat draws attention. In this context, studies are carried out with clean energy sources such as fuel cells where hydrogen is electrochemically transformed into electrical energy, and thermoelectric energy used to generate energy from heat. What is the fuel cell? Fuel cell is an electrochemical energy converter that converts chemical energy of fuel directly into the direct current electricity. Fuel cell is an energy generator. It is not an energy storage device. A fuel cell circumvents all other electricity generating processes in a single step without involving any moving parts. It is this simplicity that attracts attention. Such a device must be simpler, thus less expensive, and far more efficient than the 4-step process previously depicted. Okay, in here I will talk about the principle of fuel cell work. You can see one of the diagrams of the how to work of the fuel cell. In here, hydrogen is fed to anode compartment as a fuel, and oxygen feeds to cathode as an oxidant. Oxidation reactions at the anode and reduction reactions occur at the cathode. As a result of the total reaction, water and heat emerge as a product. Electrochemical reactions occur at the electrodes and electric current occurs. There are many types of fuel cells mentioned in the presentation. It is polymer electrolyte, membrane, alkaline, phosphoric acid, molten carbonate, and solid oxide. Each fuel cell has its own pros and cons and own applications. They usually change according to the temperature or electrolyte used. Here, PMFC is an example of low temperature because the temperature between the 50 and 100 degrees Celsius, and solid oxide fuel cell is an example of high temperature. The temperature is between 700 and 1000 degrees Celsius. In this study, we choose the PMFC. And also in here, pros and cons of fuel cell. There are many pros and cons of the fuel cell. Pros is high efficiency, good reliability, no moving parts in the energy converter, be compact in the structure, almost no emissions, no noise pollution, and fuel flexibility and smooth operation. And also there are cons of fuel cells that are raw materials for fuel cells are quite expensive. Obligation to provide hydrogen security. You know that hydrogen is flammable. And a lot of the currently available fuel cell technology is in the prototype stage and not yet validated. Now, I want to talk about thermoelectricity and given perspective of waste heat from process. That process is thermal power plant, nuclear power plant, automobile, waste incinerator, factory, and natural gas in the figure. For realized process, we need to use energy. Unfortunately, all energy is not useful because of efficiency. We are also generate waste heat. If we can catch waste heat and using into thermoelectric module, we can generate electricity. After this, we can supply the grid with the generate electricity. It will increase the efficiency all of the process. What is the thermoelectric module? Thermoelectric modules are electronic devices consisting of the semiconductor materials, one surface of which is cooling while the temperature of other surface is according to the direction of direct current. These tools are used for cooling or electricity generation. Thermoelectricity based on three basic principles that are Seebeck effect, Peltier effect, and lastly Thomson effect. The first studies on thermoelectricity were carried out by German physicist Thomas Seebeck in 1821. In that study, the electric current was circulated in a closed circuit containing metals, and the response of the needle for two different temperature values was observed. However, Seebeck did not release the basis of the study and assumed that containing heat generation creates an effect of a Q value is with the electric current circulated in the circuit. An electric current would flow continuously in a closed circuit made of two dissimilar metals if the junctions of the metals were maintained at the two different temperatures. In 1834, the Peltier effect has been found by the French physicist Jean-Charles Atens Peltier. Peltier, by placing a current through the interface of two different conducting materials, found that heat was absorbed or expelled, and electrical current will produce temperature gradient at the junction of two different conducting materials. After this discovery, William Thomson examined these two effects within the framework or thermodynamics laws and defined them as follows. When electric current is passed through the conductor, having a temperature gradient over its length, heat will be either absorbed by or expelled from the conductor. Whether heat is absorbed or expelled depends on the direction of both electric current and temperature gradient. And also, in here we look at the pros and cons of the thermoelectric modules. Pros are environmentally friendly, no chlorofluorocarbons, reliable source of energy, recycles waste heat energy, a long life, and small size and weight, electrical quiet operation, ability to generate electrical power, no leakage problem, and so on. And also cons of thermoelectric modules. Advantage only 4 units smaller capacity. More power is needed to run system. Slow technology progression and low energy conversion efficient rate and able to dissipate limited amount of the heat flux and so on. Okay, what is the aim of the study? This study is aimed to reduce the energy deficit by converting the heat energy released to nature without being used as electrical energy. For this purpose, the mathematical model of the design setup created by the principle of heat transfer laws was analyzed in the commercial finite element software. The current, voltage, and power values obtained as a result of these analyses were recorded depending on the certain boundary conditions. The literature we have examined consists of the study on waste heat recovery. In 217, Kuhn designed a liquid-cooled thermoelectric generator system to be used for waste heat recovery in the exhaust system of internal combustion engines. He observed that the obtained electrical power directly proportional with the increase of the temperature difference between the thermoelectric generator surfaces, the increase in the amount of refrigerant flow rate, and maximum power is value. And also in the same year, Morel et al. Investigated the capacity of peltier materials to be used in the cooling of electrical vehicle batteries and established an experimental setup for measuring the thermal power of the battery unit. As a result of the experiments they observed with peltier, batteries can be cooled effectively and the battery can be kept between -20 and 60 degrees Celsius, which is a floor temperature range. This study, it is aimed to obtain electricity from the waste thermal power in a fuel cell with thermoelectric power. The model design of the thermoelectric module is shown in the figure. Thermoelectric modules are the thermal elements formed by N and P-type semiconductors connected in series electrically and in parallel thermally. In this study, 3 thermoelectric modules are connected parallel to each other in terms of heat transfer. Both sides of N and P-type semiconductor materials were chosen as a copper. Also, isotropic thermal conductivity, isotropic resistivity, and isotropic seebeck coefficient has been defined by software. You can see the properties of the material. After that, the modeling thermoelectric modules model meshed it, and it has been found 12,000 meshed elements. The finite element mesh structure in the thermoelectric module. Also, since hot and cold heat sources are needed to produce thermoelectric energy, the required hot surface temperature was selected between 55 and 85 degrees Celsius with a 5 degrees Celsius interval, which are the efficient operating temperature range of fuel cell Celsius. And the cold surface was selected as 22 degrees Celsius, which is the room temperature. The convection coefficient is 1,000 watt per square meter degree Celsius. Potential values are determined as minimum voltage is equal to 0 millivoltage, and maximum voltage is equal to 80 millivoltage, and that is the voltage of the amount of the junctions. Also, boundary conditions of thermoelectric modules as shown in figure. In this study, the electrical power that can be produced by a thermoelectric material included in the system was determined by using the heat emitted by a fuel cell in the optimum operating temperature range. The results of the thermoelectric module with a hot surface of 85 degrees Celsius are shown in figure. Also, a current value of 1 ampere a power value of 20 watts was obtained. As the operating temperature of the fuel cell increases, the electrical power generated from the thermoelectric module increases accordingly. This is the linear relationship between the fuel cell temperature and generating power. And all in all, the study is valid for a thermoelectric module produced with a serial connection of 11 PN junctions. It is predicted that the total electrical energy produced will increase when the number is increased. This study, which was carried out to increase the system efficiency of the fuel cell and to provide an energy harvesting method, energy generation system from heat, is promising in terms of its results. Thank you for interest and attendance.
Thank you, Büşra Hanım, for your presentation. It seems you don't have any questions at the moment, so we can move with our next presenter, Mr. Levent Akbulut. If you are ready, you may start.
Merhabalar.
Merhaba.
Bir dakikanızı alacağım. Öncelikle merhabalar. Ben Levent Akbulut. Başkent Üniversitesi Makine Mühendisliğinden yüksek lisans öğrencisiyim. Gerçi tanıtımda yüksek makine mühendisi olarak geçiyorum ama beni daha önce mezun ettiğiniz için teşekkür ediyorum. Projemden birazcık bahsetmem gerekirse bir havalı güneş kolektörün tasarımı, performansının sayısal incelenmesi. Ama aslında projenin genelinde şöyle bir şey var. Buna gelmeden önce 5 farklı sistem incelenip bu sistemler içerisinde en fazla enerji bakımından faydalı olan sistem hangisi, buna bakılmak istendi bütün amacında. Ve bunun enerji açısından en verimli olabileceği hangisi tartışmaya açık hale getirildi. Şimdi birazcık bu işe başlamadan önce yenilenebilir enerji kaynaklarından bahsetmek gerekirse yenilenebilir enerji günümüzde oldukça bir önem taşıyor. Ki nitekim bu kadar önem taşıyor ki şu an bu konferans düzenleniyor. Ben de dünyanın bir yerinde bu konuşmayı yapıyorum. Bu kadar önemli olmasaydı bu konu hakkında konuşmazdık. Şimdi güneş, rüzgar, biyokütle, jeotermal oldukça önemli bir yere sahip. Ama tabii güneşin ayrıca bir önemi var. Çünkü güneş enerjisi sonsuz bitmek bilmeyen bir enerjiye sahip ve bu sayede de bizim için oldukça bir öneme sahip oluyor. Böyle olunca farklı sistemlerin tasarımları kaçınılmaz oldu. Nitekim ki bu sistemlerden birisi havalı güneş kolektörü. Şimdi bu benim projemde step olarak alacağım ilk sistem olacak. Çünkü bununla birlikte ayrı 4 farklı sistemi de inceleyip bir sonuca varacağız. Şimdi havalı güneş kolektörü içinden hava geçen, güneş enerjisiyle ısınan bir sistem. Bunun beraberinde ikinci sistem olarak kullanacağım sistem düz PV panel. Bu PV panelde de kazanacağım elektrik enerjisine bakacağım. Üçüncü sistem olarak da PVT, fotovoltaik termal sisteme bakacağım ki aslında projemin de ana temelinde buna yatıyor. Ama ardından da şöyle bir durum var ki bu fotovoltaik, PVT, termal sistemler nasıl daha geliştirilebilir dendiğinde de kanatçık yapılı fotovoltaik, termal, PVT sistemler. İşte bunlar benim 4 ve 5. sistemlerim olacak. Çünkü bunlar içinde de kanatçık yapılarıyla gelen havayı dağıtarak panelin soğutulması hedeflenip bu sayede de verimin artırılması amaçlanıyor. Şimdi bu 4 aslında 5 farklı sistem çünkü kanatçık yapıları 2 farklı kanatçık yapı olacağı için 5 farklı sistemi aynı şartlar altında değerlendirmem gerekecekti. Ve bu yüzden de önce işe bir yerden başlamak gerektiğinde havalı güneş kolektörünün önce bir doğrulamasını yapmam gerekti. Şimdi havalı güneş kolektörünün doğrulamasını yapmamda şöyle bir durum var. Daha önce 2019 yılında Hindistan'da saat 10'da yapılmış olan bir projeyi kendime referans aldım. Bu projeyle önce doğrulamasını yapmam gerektiğinde bütün şartları, gelen ışınım, gelen güneş açısını ve saat olarak hepsini aynı tutuldu. Yani bu 5 farklı sistemde de aynı tutularak, çünkü aynı referansta değerlendirilmesi gerekti. Şimdi ilkine doğrulaması yapıldığında bu çalışmanın analizinin sonucunu tabii ki de sonrasında geleceğim ama yine de çok küçük bir verim farkı yakalandı. 1.55'lik. Tabii bu da makaledeki bilinmeyen bazı malzemenin cinsi olsun veya farklı bilimsel nedenlerden kaynaklanıyor olabilir ama bu çok küçük bir farktı, göz ardı edilebildi. Modelleme ve tasarıma geçince de panelde de, yani PV panelinde de aynı referans aldığım doğrulamadaki modelin üstüne yerleştirileceği için aynı ölçülerde alınıp değerlendirildi. Ve PVT sistemine geçildiği zaman da zaten bu birçok insanın da bildiği katmanlardan oluşan EVA film, solar sel ve cam tabakadan oluşan sistemle birlikte bunun da modellemesi aslında diğerleriyle aynı tutuldu. Çünkü hepsinin dediğim gibi aynı karşılaştırması yapılacaktı. Şimdi kanatçık yapısına gelince 2 farklı kanatçık yapısı uyguladım bu projede. Bunlardan bir tanesi düz kanatçık diyeceğim sistem olacak. Bunlar panelin iç kısmına boylu boyunca yerleştirildi ve dediğim gibi gelen havayı dağıtmak, amaç paneli yüzeyini daha çok soğutmak, çünkü verimi artırmak. Fakat burada işte 2 farklı kanatçık yapısı olunca acaba hangisinin daha verimli olacağını birazcık da deneme yanılma yoluyla, öngörüyle de belirlemiş oldum. Bunlardan birisi düz kanatçık yapılı sistemken diğeri kaz ayağı olarak kanatçık yapılı sistem oldu. Ve bunları, bütün bu 5 farklı sistemi de ANSYS programı kullanarak bir ısı bakımından değerlendirdik. Şimdi bu 5 farklı sistemin sayısal incelenmesi, sıcaklıkları, ortalama panel sıcaklıkları belirlendi ve havalı güneş kolektöründe giren ve çıkan havadan elde edeceğim ısı enerjisi, PV panelinden elde edeceğim elektrik enerjisi ve PVT sisteminden aslında hem elektrik hem ısı elde edeceğim için çok verimli gözükse de bunun daha da geliştirilmesiyle birlikte kanatçık yapılarını da incelemiş olduk. Şimdi bunlardan ilki en üst sağ köşede gördüğüm benim havalı kolektör. Havalı kolektörden geçen ısı sıcaklığı. İkincisi PV sisteminde. Tabii 2 ile 3 arasında oldukça bir fark var. Çünkü PVT sistemlerde panel sıcaklığını daha çok düşürüyoruz bu sayede geçen havayla birlikte. Bu da bizim oldukça işimize yarayan bir sistem haline dönüşmüş oluyor. Fakat bunu biz daha da nasıl soğutabiliriz düşüncesinde kanatçıkları eklediğimizde işte böyle bir fark gözüküyor. Bu bize aslında kanatçığın daha gerekli olduğunu ve kanatçık yapılarının da kendi içerisinde çok daha önemli yere sahip olduğunu gösteriyor. Şimdi bunların sonucunda aslında havalı güneş kolektöründe hava giriş sıcaklığını görüyorsunuz tabloda. Ve ortalama panel sıcaklığını, ısı verimini ve güç değerini. Şimdi havalı güneş kolektöründe ısı %18.45'lik bir ısı verimi elde etmişken fotovoltaikte bu %30. Kanatçık, düz kanatçık yapıldı %32 ve kaz ayağında daha da artarak çıkmış oluyor. Yani bu aynı şekilde elektrik bakımından baktığım zaman, yani güç değerine de baktığım zaman da aslında bunda da bir artış olduğu gözüküyor. Yani benim için burada en sonunda baktığım sistemde kaz ayağı kanatçık yapısı havayı daha iyi dağıttığı için panelin çıkış sıcaklığıyla etkileyip paneli daha çok soğutuyor. Bu yüzden kaz ayağı kanatçık yapısı benim sistemimde aslında en gerekli kanatçık yapılı sistem olmuş oluyor. Fakat bu şöyle bir sonuca da varılabiliyor aslında. Şimdi bunun sonucunda bu sistemde elde edilen güç değerinde %7.88'lik bir artı sağlanırken elde edilen ısı veriminde de %19.85'lik bir şey sağlanıyor. Fakat şimdi bu güzel kanatçık yapıları bizim için fotovoltaik termal PVT sistemlerinde oldukça gerekli ve verimli oldu. Aslında bu birazcık da ucu açık bir şeye dönüşüyor. Çünkü kanatçık yapıları oldukça şekillendirilebilip daha çok da geliştirilebilir. Bu sayede de bu bizim sistemimizde daha iyi yöne de gidebilir. Bu tabii belli bir yere kadar, belli bir yerden sonra sizin çıkış hava sıcaklığınız çok küçük farklarla oynasa da yine de bize gelecek için bu sistemlerin daha da geliştirilebileceğini gösteriyor. Ama benim projemde şu an için bu kaz ayağı kanatçık yapılı fotovoltaik termal PV sistemlerinin en gerekli ve verimli sistemler olduğunu gerekli incelemenin sonucunda varmış olmaktayım. Ve bu yüzden de bu elde ettiğim sıcak hava işte çeşitli alanlarda kullanılırken bunun yanı sırasında elde ettiğim elektriksel sistemin çalışması ve sistemin dışında da kullanılmış olarak sağlanmaktadır. Bunun neticesinde de beni de dinlediğiniz için teşekkür ederim. Genel olarak da projem buydu. Teşekkürler.
Thank you, Levent Bey. We can, if there's no questions, let me check.
Herhangi bir sorum yok bende gözüken.
Okay. Then we can move to our next presenter, Nurayni Sunasi from International University of Cyprus. If you are ready, you may have the floor. Nurayni Sunasi.
Hello. Can you hear me, please?
Yes.
Okay. I'm trying to share my presentation.
Okay.
Can you see my presentation?
Yes, we see it now.
Can you see my video as well?
Yes, there's no problem. You can start.
Okay. Can I start?
Yes.
Okay. Hello, everyone. Good afternoon. My name is Renewable, student from Cyprus International University. I'm here this afternoon to present our research on the design of off-grid PV electricity generation system for residential lighting and income generation activity of the community.
Mr. Sunsi, we don't hear you very well.
Okay. Can you hear me now?
Now it's okay.
Okay. Let me start. As I have said earlier, my name is Nurayni Sunasi, student from Cyprus International University. I'm here this afternoon to present our research on the design of off-grid PV electricity generation system for residential lighting and income generation activity of the community, Somali local government, Kano State, Nigeria. This is the content of my presentation. In here, I have abstract, introduction, material and method.
Mr. Sunasi, sorry to interrupt, but can you put it to full screen, please?
Okay.
The presentation.
Okay. Sorry, please, I'm trying to put it to full screen.
Okay. No, it's worse. I think it's F5 button, but.
Like in my system.
Okay, if it doesn't work, okay, you can continue then.
I don't know what happened.
I can guide you, Mr. Nurayni. Could you please click slideshow on the top of your screen?
Okay, slideshow, yes.
And from there, click from beginning on the left.
Okay, here?
Yes.
Okay. Is it okay now?
Yes, it is full screen now. Please go ahead.
Now it's okay.
Okay. Can I start from the beginning or I can continue?
You can continue. No need to start again.
Okay. Like I have said earlier, this is the content of my presentation. I have abstract, introduction, material and method, result and discussion, conclusion and references. So in my abstract, the reason why I bring my abstract is in case if someone is interested in the paper, it can go to. This research is aimed at addressing the suffering of the Yetio community smaller local government, because the Yetio community is located in a remote area of smaller local government, and until now they don't have electricity. That's why we come up with the idea of designing an off-grid PV system so that we can propose the design and end the suffering of the Yetio community. And in this research, a formal software was used for the simulation and optimization. And also, the result of the design shows that a total of 11.115 megawatt hour per year can be produced at a total cost of 4.8 million US dollar. And in this design, we consider a lot of innovation tools, unlike other existing literature in the off-grid PV system, like technology, innovation tools, business model, market design, and system operation. And also the detailed cost of this design was given. So in the introduction, as I have said earlier, most of the rural area, including the community, smaller local government, the supply of electricity is mainly from the fossil fuel. So there is need for most of the rural area that didn't have access to the electricity to be transformed from old or traditional fossil fuel sources to the renewable energy. And the key reason why we come up with this idea is because to address the suffering of the community. Our generation is fluctuating between 3,200 megawatt to 4,000 megawatt out of 12,522 megawatt total installed capacity that we have across the entire nation. The reason why of this fluctuation, because most of the power sector that we have, only 2 of them out of 25 power sectors that power installed generation capacity that we have in Nigeria, out of 25, only 2 of them are purely renewable, are from the hydropower. Others are from the coal and natural gas. So it's need for Nigeria to shift from this old method. Why? Because in Nigeria, as I have said earlier, the total installed capacity that we have is 12,522. But our current generation is fluctuating between 3,200 and 4,000 megawatt, because our power sector are facing a lot of challenges, mainly, such as maintenance, repair, vandalism, leakage from natural gas pipeline. That's why the total installed capacity cannot be injected to our national grid. That's why in Nigeria, according to the World Bank 2004 report, that Nigeria is among 31% of the sub-Saharan African region that are suffering from electricity generation, transmission, and distribution. So in Nigeria, there is still community, just like the air community, they have solar potential, but they are not connected to the electricity grid. And also the air community, they have agricultural activities, they have many local activities that they need electricity to process them. So there is a need for the air community to have access to the electricity. That's why we think of designing off-grid solar PV system, because until now the air is not connected to the Nigerian national grid due to the political lack of political will. So that's why there is need for the air community to have an off-grid system so that the agricultural and commercial activities will be forged ahead. Next slide. So material and method. first and foremost, as I have said earlier, a HOMA software was used in this design. First and foremost, if you look at figure one, this is typical area community location. So this figure is obtained from the HOMA software. The exact location of the area community is 11 degree, 20 minutes, 8.33 seconds, and north, and 8 degree, 53 minutes, 52.64 seconds. And Gedia, as I've said, is located in a remote village of Somali local government with a lot of agricultural potential and also solar potential. If you look at figure 2, this figure 2 is showing the average solar radiation of Gedia community per kilowatt hour per meter squared per day. So in a nutshell, Gedia community, they have nearly 5.22 kilowatt hour per meter squared per day solar radiation potentials. Then load data analysis, how we come up with our load design. So in this design, we consider a typical rural area load, and also our sample size is based on the existing literature on off-grid solar PV system. So Gedia community, the sample size, the total number of houses in Gedia community, as you can see from this figure, they have 150 houses, residential houses, because as I've said earlier, this project is aimed of providing electricity for residential lighting, for usage of lighting purpose, radio, fan, and socket outlet, and refrigeration. So this is a total load for 150 houses. Then commercial load. Commercial load, we further divided commercial load into 4. First, we call it commercial load, where shops, irrigation pumps, water pumps, welding, their load are calculated. Then industrial load. As I've said, Gedia, they engage in rice farming, cassava farming, and maize processing. So it's good for them to have electricity access so that at least at a local level, they can have a factory that can be processing rice, maize, and cassava. Then hospital and school are also considered as a commercial load. So the total power obtained from this load analysis was 2,587 kilowatt hour, and here is in megawatt hour, kilowatt hour. So after calculating the total power demand of this Gedia community, we assume that if at all 80% of the load are likely to be connected at a time, that's why we consider 80% diversity factor, percentage of the load that is likely to be connected at a time. Then in the next slide, you can see the schematic diagram of the installation. So in this design, because we are trying to come up with off-grid photovoltaic system, so for us to make our decision, we have to consider the current situation. As I have said, the air now, as at now, they use fossil fuel to generate their electricity. So the first model, we call it model 1. We model our data based on the input requirement that we have, Gedia community load and Gedia commercial load. So this model is a fossil fuel based model. Well, the second model is a renewable based model, whereby solar PV is used, and I made mention of innovation technology. So one of the innovation technology that we use lithium ion battery for the storage of electricity in case during a cloudy weather or during night hour, so that we can have a complete supply for 24 hours period. Then inverter was also used for converting a DC current to AC current. So in the next slide, for us to have our model, because for us to have our model and for us to have a good optimization result, we need to have our input requirement, or we need to have our component for this simulation. And for this purpose, we have battery, we have power inverter, we have PV model, and auto size genset for a fossil fuel based model. Then result and discussion. So as you can see from these two figures, figure 5 is a fossil fuel based model. This represents the total cost of the fossil fuel based model. This is the total cost. The capital cost, replacement cost, operation and maintenance are provided. And if you can see this rate, this one is a salvage. We call it a scrapped or salvage value. And this salvage value, if it is high, that means if the salvage value is high, that means the scrapped value is overestimated. And if the salvage value is low, that means the net income is understated. Also in figure 6 is representing the total cost of the proposed PV upgrade system for usage of the area community. As you can see from these two figures, the fuel cost of this model is nearly equals to, is even more than the total cost of the renewable-based model. That's why renewable-based model is the best model. Apart from the carbon dioxide emission and other factors, even the operational cost, the fuel-based model, oil fuel cost is even nearly equals to the total cost of the renewable-based model. Then electricity consumption and production summary. This table 3, represents the total electricity consumption and the electricity production summary. As you can see from this table, the unmet electrical load of model 1 is 0. Why is it 0? This unmet electrical load, it means that if the electrical demand exceeded the supply, so that means you can expect the unmet electrical load. But in this model, because it's just a fossil fuel, it has no weather interruption or anything, that's why it's not 0. And this table also, table 4, is representing the financial analysis of the two models, model 1 renewable-based and model 2 solar-based model. As you can see, the simple payback period of this model 2 renewable-based is that the project can pay back within less than 2 years. Within 1.5 years, the project can pay back. Then greenhouse gas emission result. So based on the optimization result or based on the simulation result, it was found that the model 1, if at all a solar upgrade PV is to be used by the community, a total of 1.98 million kilogram per year of carbon dioxide only can be saved. So that's why it's good for us to shift from old fossil resources to the renewable-based solar resources. So in conclusion, the main aim of this research work is to design a solar upgrade system for residential usage, for residential lighting, and also income generation activities of the community. And also in this design, a HOMA software was used for the modeling, simulation, and optimization. And also the result of the optimization show that the entire system can pay back within 1.5 years. And also a system can save nearly 1.9 million kilograms per year of carbon dioxide emission. And also, if this project is properly implemented, there will be, it will create a lot of job opportunity for the community and the nearby villages. And also, it will help to reduce the carbon dioxide emission for the community. And also, if this project is executed, it will also help for for reaching zero with renewable in a remote area like the air community, and also bridge the gap of electricity access in the remote areas like the air community. Then these are the references that we use for this research work. Thank you very much. And at this point, I would like to thank Tanai Hodian for his tireless effort and commitment to see that we learn how to integrate renewables to our villages and to our cities. Thank you very much for all the participants. Thank you.
Thank you for your presentation. And I think we can move to our next presenter, Rania Hamemi from National Engineering School of Tunis.
Hello.
Hello.
Hi. I'll share my screen.
Yes. Please put it to full screen as well, and then you can start.
Yeah. Is it full screen or?
Right now, no, you need to start the presentation. You can go to slideshow at the top.
Mm-hmm.
Yes.
Okay.
Just give it a second. Yes. Okay. Now we see you can start.
Okay. Hi, everyone. I'm Rania Hamemi. I'm PhD student from Energy and Laboratory from National Engineering School of Tunis. Today, I'm delighted to present my work, which is exergo-economic analysis and multi-objective optimization of the solar combined system, organic Rankine cycle, and ejector. Yeah.
I'm sorry to interrupt you. Could you move the Zoom menu from your screen away? We are seeing it as a gray box, so it is obstructing your.
How to hide self-view? This one?
I guess so. I'm not sure which menu it is because we see it as a gray box, but you need to minimize that.
This one?
Yes, that one.
Yeah.
Okay, that is good enough. Sorry to
Okay.
interrupt. Please go on.
No problem. Yeah. So we will begin with the plan of the presentation. So we have the introduction, overview of the system, energy, exergy, exergo-economic analysis, and multi-objective optimization. Then we have the results of the base case and optimal case, and finally with the conclusion. So let's begin with the introduction. We are all aware that power consumption is increasing a lot during the past few decades. So using renewable energy has acquired a big and great interest. So in this work, we're going to implement solar energy in our system to produce cooling effect and to generate electrical power. So for the study objectives, we're going to evaluate the system with conducting energetic, exergetic, and exergo-economic analysis. We're going to implement the simulation of the simulation results of the parabolic graph solar collector and the system evaluation. And we're going to focus on the multi-objective optimization of the system to obtain optimal values for the design parameters. So as you can see, this is the overview of the system. So the system is composed of the ejector refrigeration system, the organic Rankine cycle, and the heat transfer fluid system. So as you can see in point 16, the heat transfer fluid will get heated from the sun, from the solar radiation, and the heat will transfer to the steam generator where the working fluid will be heated as well. For the parabolic graph solar collector, we have conducted a mathematical model for this solar receiver, allowing the control of the outlet temperature of the heat transfer fluid in our previous work. So the simulation results of the solar receiver, which are calculated hour by hour from sunrise to sunset, are introduced in the simulation of the combined system. For the ejector as well, we have conducted a mathematical model in our previous work. I have mentioned the previous work in the paper, in the communication that I have sent it to you. So for the ejector, the main parameters are the thermodynamic parameters, which is the entrainment ratio. We have the driving pressure ratio, the compression ratio, and for geometric parameters, we had ejector area ratio and the diffuser area ratio. So let's begin with the energy analysis. So for the energy analysis, I have conducted the energy analysis for all the components of the system, of course, but I have just mentioned only the evaporator and the turbine. Here, the cooling capacity of the evaporator and the power produced by the turbine, the coefficient of performance of the system, and the entrainment ratio of the ejector. I can't mention all the components because it's going to be very, very long presentation, so that's why. For the exergy analysis, so exergy analysis is an extension of energy analysis. It takes into account the quality of a given quantity of energy. So it's a powerful tool to better understand our system. So we have conducted this analysis on a component level with exergy of fuel and exergy of product. As you can see, exergy of fuel of component, it's the sum of exergy product and exergy destruction for each component. Also, for the energy analysis, I have just mentioned the evaporator, turbine, and the total system. So for the evaporator, for example, we have for the exergy product of the evaporator, it's exergy in stream 18 minus exergy in stream 17. For the fuel is exergy in 0.8 minus exergy in 0.9. And for the exergy efficiency for the component, the evaporator, it's the ratio between the exergy product and exergy fuel. For the total system, exergy product of the total system is exergy product of the evaporator plus the net power output of the turbine. For the exergy fuel of the total system is exergy fuel of the steam generator, and for the total exergy efficiency of the system is the ratio between product and fuel as well. For the economic analysis, which is very important also to evaluate and cost optimize an energy conversion system, it's an economic analysis is required. Well, there is a lot of steps for the economic analysis, but I will not detail them. But for the first step, we have the estimation of the purchased equipment cost. For each equipment, we have to estimate the purchased equipment cost using cost estimating charts. For the second step is the estimation of the installed equipment cost using bare model factors. Those bare model factors, we can find them also in the cost estimating charts. The third step is the estimation of fixed capital investment, operating and maintenance costs, and fuel costs. Well, for this third step, we had a lot of formulation and equation and percentages. We can find it in details in the book of thermal design and optimization of Pejan. For the exergo-economic analysis, it is a unique combination of exergy and economic analysis. It is a powerful tool to identify hidden costs associated with a system that cannot be identified using conventional energy, exergy, or cost analysis. So it is crucial to the design of a cost-effective system. So as well, for the exergo-economic analysis, we have conducted on a component level. We have developed a cost balance for each component of the system using cost of fuel, cost of product. As you can see, so the cost of product of each component is the sum of cost of fuel of the product plus the cost rate of the component that we have conducted from the economic analysis. As well, I've just mentioned evaporator turbine total system. So as you can see, for the evaporator turbine, for the total system is the cost of product of the total system is the product of the evaporator plus W net power output of the turbine multiplied by the cost of shaft work, and cost of fuel of the total system is cost fuel of the steam generator. Well, for the multi-objective optimization, the goal of the multi-objective optimization is satisfying conflicting objective functions simultaneously. It's an appropriate and practical tool to determine the optimal solution and optimal design parameters for the system. Well, in our system, we have two conflicting objective functions, which are the total exergy efficiency of the system that we want it to be maximized and the total product unit cost of the system that we want it to be minimized. So to can afford that and to can realize the multi-objective optimization, we have to choose some decision variables that that can affect on the performance of the system. each range for each decision variables. So for example, we have the evaporator temperature, yeah, the ratio of extraction, the isentropic efficiency of the turbine, ejector entrainment ratio, evaporator cooling capacity, the turbine expansion ratio, evaporator coefficient, condenser, preheater, and steam generator coefficient. So for the results, we begin with the base case. So as you can see, so this is the hourly variation of the temperature of the heat transfer fluid. It depends on the global radiation. Depends on the global radiation. Yeah. So the heat transfer fluid recovers thermal energy in form of heat and transfers it. Therefore, it can be used in the system. So the highest temperature generated, it's obtained between 1 p.m. and 3 p.m. Well, we have conducted this with this figure is for the 21st of June, is the longest day of the year. We have worked with this day, and the best temperature is 141.25 degrees Celsius, which is between 1 p.m. and 3 p.m. So MATLAB computer program was developed for the simulation of the combined system. So as you can see, this is the operating condition of the combined system. We have worked with the working fluid, which is isopentane, and temperature evaporator, etc. And the temperature of the heat transfer fluid, as I said, is the best temperature. It is at 2 p.m. and 21st of June. So the performance of the combined system, the net power output is 146 kilowatts, entrainment ratio is 0.19, and the coefficient of performance of the system is 0.17. Okay. So after that, we have conducted the hourly variation of the temperature of the heat transfer fluid of the solar receiver is used to visualize the performance of the combined system. So as you can see, the first figure is the hourly variation of the coefficient of performance and total exergy efficiency. So the coefficient of performance and the total exergy efficiency varies during the day. They reach the minimum value in the middle of the day. For the next figure is the hourly variation of the total exergy destruction and total exergy efficiency. It's clear that the highest exergy destruction occurs between 1 p.m. and 3 p.m. They are inversely proportional with the exergetic efficiency of the system. So here, the hourly variation of the total product unit cost. So it can be seen that the total product unit cost rate is the highest at the beginning of the day, at the end of the day, but the minimum value it's in between 1 and 2 p.m. Now we move to the optimal case. Well, we have used MATLAB optimization toolbox. We have used genetic algorithm in MATLAB. So those are the results of the optimization. Well, this figure is the Pareto front of the optimization that we have conducted. So as you can see, this is the selected optimal design point. Well, the exergy efficiency and the total product unit cost selected at the selected point are obtained as 66.85%, and for the total product unit cost, $0.136 per kilowatt hour. Well, for the design parameters, the decision variables that we have chosen at first, those are the design optimal values that we have found. So as you can see, they are totally different from the beginning. So here it's a comparison between base case and optimal case. So for example, for the net power output, for the base case was 146. Now for the optimal case, it became 190.2 kilowatts. Well, for example, for the total exergy destruction, it was 126, became 90.66 kilowatts. Total exergy efficiency, of course, and the total product unit cost. They are ameliorating. Yeah. For the conclusion, So we have implemented a solar energy injector refrigeration system combined with an organic Rankine cycle for the simultaneous production of cold and electricity. So we have evaluated the system from energetic, exergetic, and exergo-economic point of view. We're taking into account the hourly variation of the heat transfer fluid temperature of the solar receiver. And we have conducted the multi-objective optimization to obtain optimal design parameters of the system. Thank you for your attention. If there is any question.
I think there is no question at the moment. So thank you for the elaborate presentation.
Yeah.
And our next presenter is not here due to a health issue. So I think that was it. We can wrap it up. Hocam.
Okay, thank you very much, Anil, our General Secretary. You are individual in your work, also doing good work for this transition. And the young people should take initiative on this. It's time for us to go and you should take the initiative. Thank you very much for your contribution. Thank you to Nuraini, Levent, and Bushra and Rania. Thanks for their contribution. Now we shall have a 5 minutes break. Then after we will make a closing session and we will just evaluate and we will get your inputs for how to improve the next conference and what were the mistakes we have made, what topics would you like to be included next time. These are the things we will be talking. Please stay with us. And in 5 minutes, now it's 15:16, so 15:20, maybe 25, let's say, in 6 or 7 minutes, let's meet again to discuss whole conference. What was good, what was need to be added, how we can improve this. Because each year we do this, and with your contributions, we make better conferences. Thank you very much, Anil, again.
Thank you.
See everybody next 5-10 minutes. Let's say 15:25. 15:25 we meet again. Good. Evet. Yes, now almost we are at the end of our conference. Now this is an closing session, but I would very much appreciate, and Alper Saydam is here, and he is really the person who is making this meeting possible online. Last year also we did it together. I would like to thank him for his contribution and the capacity to do this also. It's a very big happiness for us to work with Alper. Now I would like to go one by one. Let me see how I can see the gallery view. Yes, now we are here. Now I would like to ask Alper from you when people raise their hands to give the floor to them, and we will note. And we know that we don't have Turkish translation now, so English-Turkish translation. So the people who would like to express their feelings in Turkish, they're also invited to do that. I mean, we will note these assessments also, and they can also use the chat to include their suggestions and in the question and answer session also. Now we want to give the floor to the participants and to hear about them. How do they feel and how can we improve this conference, because we have already decided to organize it between 9, 10, 11 June 2022. And we also put a title of it. Maybe you can show the title to the participants. Can you just share the screen, Alper?
Yes.
Is it possible?
Yes. Just a moment.
I can also share if you like. I'm ready for it.
Okay. Is it visible?
Okay, you did it already, huh?
Yep, I did it.
Okay, very good. So there are some shades on it. Can you see this also?
I'm moving down.
No. Okay. Now I think it's clear. Okay, Alper, that's clear, huh? Okay. Now that's the title we put. Can people see this now?
No, I stopped sharing. Do you want me to put
Okay, just put it. So I just want to go through the name only, and then continue.
Of course. Okay, it should.
Okay, so the next year we are talking about a transition and what to do about this transition, and all United Nations, Renewable Energy Agency, and European Green Deal, and everybody is talking about this, and the renewable energy is increasing, and we are talking about innovations to implement. So about 1,500 consortiums established to kick off this European Green Deal. So we believe that next year, in 1 year, we can talk about the status in global energy transition. What are the achievements and what was the barriers to overcome, and what are the innovations implemented, and what will be the future perspective towards 2030 and 2050. That's the approach we have, and we will inform you people who want to participate about the topics later. Thank you, Alper. So now let's hear about the participants, and let's note so that we make a better conference for the next year.
Yeah, there is a suggestion in the chat that Engin Özdemir suggests that energy storage and smart grid issues should be included but I guess it will be included because achievements barriers and the main barrier is the energy storage systems. So
Yes.
I believe that it is unavoidable to talk about it. Hocam, what do you think about this topic?
Yeah, that I agree, because when we have with European Renewable Energy Association, Eurosolar, about 14 years ago, we have initiated this International Renewable Energy Storage Conference. Maybe you can share the link with the audience. So it was important before, and today, yes, it is important, as Professor Özdemir is mentioning, because if we do not store renewable energy, then we cannot make the solution, renewable energy, independent from fossil fuels, which is the problem. So that's correct, and we should spend more effort to include more people to attend and make submissions, a keynote maybe in the next conference. Yes, that's very good, well taken. I have seen Nuraini was asking, raising hand. Mr. Nuraini, where is he? He was went.
Nurain, I just allowed you to unmute
Hello,
yourself.
Hocam.
Okay, yes.
Hello, Hocam.
Hello, Nuraini. You want to say something? I think you raised hand.
Yes, Hocam. I just like to thank, because this is my best experience to attend the international conference. So I would like next year to participate, so that at least I can bring my quota to this remarkable achievement.
Okay, we want you, the participants, to mention about the things which didn't go well, and ask you to warn us to improve those things also. Like storage was missing, as Professor Özdemir said. We want everybody's contribution on this.
Okay, Hocam.
And we can even go by line. I know I can ask Abdullah Alperen Okumuş, for example, what he thinks about the conference and what are the suggestions from him. Abdullah Alperen Okumuş, are you here? Okay. Alperen, Abdullah, do you have any suggestions for us? Bize herhangi bir öneriniz var mı konferansın iyileştirilmesi için? Ahmet,
he's not here. I just allowed him to unmute himself, but
okay. Ahmet Durmayaz.
Hello,
Yes.
hello, Hocam.
Yes, Nuraini.
I have one suggestion.
Okay, please go.
Yes, I noticed that, Hocam, in this conference, I noticed that people from Sub-Saharan Africa, I think I'm the only participant, if I'm not mistaken.
Yes, you are right.
So,
we had a speaker, but he became...
Yes, as a speaker, I think it would be good for this conference to invite many participants from Sub-Saharan Africa, especially Nigeria, whereby we have renewable energy potentials, and we have a lot of renewable energy research centers, so that they can put a hand on deck to see that they contribute immensely to this remarkable achievement. Thank you.
Okay, thank you. We will, you will name us the people who are doing, so we will invite them to attend. Thank you, Nuraini.
Okay, Hocam, thank you.
Okay, so I see Ahmet Durmayaz here. Is he here? Ahmet Durmayaz. We would like to...
It would take a lot of time to ask everybody one by one.
Okay, is there anybody else who wants to say something over here? quick.
I see a hand.
Okay.
Rani, I'm allowing you to unmute yourself.
Okay.
Yeah. You can hear me?
Yes.
Yeah. Well, I'm delighted to join you and to participate in IRENEC. It was a very fruitful experience. Well, just my suggestion is, for example, for PhD students or master students, if we could see their submission papers, so to better understand their presentation, so we could ask questions. For example, when I see presentation of any master students, I couldn't know all the details, so I could not ask question to better understand. So I don't know if you understand me, my point of view. If we can share, for example, before they or after before seeing their presentation, if we can see their submission papers first, so we can understand all the details of the work, then we could ask question.
Okay, I mean, this is also possible. We have collected almost the full presentations and we will publish it. But your suggestion is that to put the limit of submissions a little bit earlier and make it ready before the conference.
Yeah, that's my point of view, because there is no question, for example.
Somebody can publish it before you, so you lose the copyright to your paper. And if I ask all the authors to be done with finalize their papers 1 month ahead of the conference, I guess half of the authors will not be able to do that. That is why we can only publish the abstracts on the speaker's page and not the full paper.
I'm
not sure how to overcome that.
Yeah, my comment is this. Rania wants people to ask questions, but the unavailability of the paper may not be the only reason for this, huh? Because people may not concentrate to your topic more as you are concentrating, as your expectations. This is another factor, of course. And also we put some time limitations also. But these things are happen. But when there is no question, sometimes people think that they did make a very good presentation. Everything is well understood. So that there are different reasons for this. But thank you. We can make little bit extended abstracts, Alper.
That's what I'm going to say. For example, an extended abstract with some, not all the details, but just few details on the work, for example. Yeah.
Okay.
Okay. Thank you. Thank you very much.
Thank you.
Thank you.
Okay. We have 2 people raising hands.
Yeah, Ahmet Durmayaz is raising his hand. Okay, Mr. Ahmet.
Okay, can you hear me?
Yes, we do hear you.
Okay, my name is Ahmet Durmayaz from Istanbul Technical University. I'm the advisor of Mert Çolakoğlu. Okay. I would like to say that selected articles are actually real motivation for PhD students, especially. So if you can form them in extended abstract form, this would enable to the student to publish it after the Congress, okay? And so I'm suggesting that extended abstract instead of full paper submission, okay, would be better. Say I'm telling that, say for example, 4 pages or 3 pages, etc. Page limit. I'm telling, and the second one is if you declare the number of selected articles before the conference, I think if you consider my 2 suggestions together, so, in this case, there would be much more attendant regarding especially PhD students. This would be better, not full paper instead of full paper, extend the abstract. Okay, and the number of selected articles declaration before the conference would be better. Okay, thank you.
Okay, thank you very much. One thing is we have informed all the rector offices of all universities in Turkey. So just knowing that this new information, not only the papers from the graduate students and conference papers, the others are the presentations, keynotes, and other industry papers, shows the recent state of technological development. So any master, any PhD work must be built on this new information. So that's why, free of charge, we wanted all the people doing academic work and working in the municipalities to attend this conference. We had about 600, 1,000, of course, people attended in four days, and it will be in the YouTube also. It's not too late, but we need to inform all our people, all the university students, PhD candidates, about the new developments. It's like a literature survey for them. The storage and everything, hydrogen, the Green Deal things. So, but your suggestions also are very valuable, and we will follow on this. Thank you very much. Thank you very much.
Kudret Avcı mentioned some things in the chat. I would like to translate it a bit for the English speaking attendees. That he says that thank you very much for this conference, and even though it's not in my expertise area, it was very enlightening for me. And he says that some of the presentations was very limited. It was like a summary, so we couldn't get much details from that. So he also says that it was the breaks was really short, so it was hard to follow that 4 days in a row. I would like to comment on that because most of the papers presented here are the end product of the students' master thesis or PhD thesis. So it is at least 2 years of research. And they have 15 minutes to present that. It will be a summary anyway. So it is. I do hear your suggestion that of course it is a summary in the end, but if we allow them to speak like half an hour, we cannot finish this conference in 4 days. It would be for like 7 days long, and it is already hard to follow that 4 days in a row. I agree with you, but I suggest that you can watch the videos on YouTube. It is already on the YouTube, and I'm going to cut all the sessions and upload them one by one, so you can select and rewatch any of them. So it will be a good source of knowledge on YouTube as well. So it will be easier to follow maybe from there again. If you miss some of the sessions, you can rewatch them on YouTube. I will send an email to all the attendees about it. So don't worry about trying to search and finding the videos.
And last year's presentations also are in the YouTube, last year's conference, so we should do it both. And I remember when the time shortage in United Nations meeting, once I was speaking on behalf of the civil society, and they said, I have only 2 minutes to talk about the energy problem. So, I mean, I managed, but it was such a constraint. So, I mean, as Alper said, we need to make more people participate, and the full papers is because of this, and full papers will be available for the people. Thank you very much. Who else we have?
I see the Vice President Erhan Çakar is here. Maybe he would like to.
Yeah, contribute.
Mr. Çakar, if you want to say something, please raise your hand so I can allow you to talk. Yes. Okay. Oh. Sorry. Okay, Erhan Bey, kendinizi unmute yapabilirsiniz.
Okay. I think we had another successful meeting conference this year as well. Of course, we we need to develop for future. I agree with some presenter informed that or the participants would like to see which we were doing this in our previous conferences by giving in our program booklets during the conference. So maybe we can put these summaries and we can present these in the intervals or sent previously as a program to the participants who registered, so that that can be useful for the people who ask the questions. For the contents of the conference, yes, it was again full of all the subjects, but maybe we could add for the next one also next ones we could add the recent technologies as storage of the energy, and also we should be more concentrated energy efficiency and applications of this now to reach the net zero 2050. So we can put more efforts and more presentations on these subjects. I think it will be beneficial for this. So I thank you also as a Vice President of the Eurosolar Turkey. I thanks all participants, and I hope we will meet again in next year and next years in futures. Thank you.
Thank you very much, Erhan. We have prepared already the conference program book. It's available, but also we will send them to all participants. Additionally, in the speaker session, after each speaker picture, we have the abstracts of the speeches from the conference. So not all of them, but we have the ones who have sent their abstracts. Thank you very much. And meanwhile, I would like to ask, thank over here before the next speaker to our executive committee, Erhan Çakar, Anıl Türkünoğlu, and Uğur Baş, and Ahmet Kaliber, who is supported the conference with their decisions. And also we have a graphicer, Serdar Tan, who is part of the participants now, because he is doing a very good work in preparing all our material, and our visual face is Serdar. Thank you very much to him. And our office people, we have Işıl Hanım, who is doing the contributions of all administrative things. Thanks to them, we managed to make this conference. Okay, now the next. Who do we have? Anybody else to say something more? No?
By the way, I missed Mr. Özdemir's message on the chat. He says that he can do a speech about on this topic on next year's conference, like energy storage and smart grid technologies and challenges for 100% renewable energy application. I guess we can get in touch with him within this year.
Of course, of course. And also he can organize about 4 colleagues from Kocaeli University to make a session even. That's possible. I mean, if we get abstracts on this, how to implement this storage in many scales, house scale, utility scale, this would be very good. And Professor Özdemir can lead in preparation this session. That would be very kind. As Professor Sulukan chaired this energy decision support tool development session. That's very good. Thank you very much, Professor Özdemir. Our General Secretary, Anıl Türkinoğlu, you have something to say additional?
Hello. Not very much, but I think since 2 years doing this Congress as a online webinar kind of was a great success. I think all our members, and especially we need to say thanks to Alper who did a great job at organizing the technical background, and all our he was a solution to all our needs. So thank you, and I hope we will have growing numbers next years, quantitatively, also in quality of the papers and so on. So I'm hopeful for the next years.
Thank you. Thank you very much. I would like to give the word to Serdar Tan, if he's here, to tell us about what his expectations are from the people. Serdar'dan biz şeyi isteyelim, bize bizlerden beklentisini söylesin, eleştirilerini söylesin. Bu güzel şeyi yaparken biz nasıl katkıda bulunabildik, nasıl bulunamadık onları ifade etmek ister belki Serdar buradaysa. Serdar, duyuyor musun beni?
Mikrofonunu açma etkisi verdi ama belki hocam...
Belki de şu anda müsait değil, olabilir. Teşekkürler tekrar Serdar'a da. Evet, thank you very much to everybody. As I understand, there are not too many big critics, but we will send the questionnaire to you, and we would like to have your critics and suggestions for better organization and better transition to better contribution of us to the future conferences and in our countries. So this is an interaction platform. We need to evaluate together. We need to collect our information. That's why we can define the problems correctly and find solutions which can be implemented. Thank you very much to everybody. Thanks to my team. We have already thanked yesterday the translators, and thanks for your time. And let's stay together, and we will inform you continuously about Eurosolar Turkey activities. If anybody wants you to contribute, to be a volunteer and contribute to Eurosolar Turkey, you can find from our webpage this possibility of contributing and taking part in our activities. Thank you very much. Thank you, Alper, again. Thank you to our executive committee who made the decisions for us to make this implementation. All have a nice weekend, and thanks for your time all weekend we were together. Bye-bye.